So for a single phase transformer of E1 dash E2, so basically E1 is called as the RMS value of the EMF induced in the primary, and E2 is called as the RMS value of the EMF induced in the secondary. These are basically the rated values. And LP is called as the self-inductance of the primary winding. So LP is called as the self-inductance of the primary winding, and LS is called as the self-inductance of the secondary winding, and M is called as the mutual inductance between the primary and the secondary windings, and LP is called as the leakage inductance of the primary winding, and LS is called as the leakage inductance of the secondary winding, and LM is called as the mutual inductance referred to the primary side. LM is called as the mutual inductance referred to the primary side, and LS dash is called as the leakage inductance of secondary winding referred to primary side. So now as E1 by E2 is equal to N1 by N2, and here LLP is called as the leakage inductance of primary winding. So LLP is nothing but it is a leakage inductance of primary winding is equal to LP minus M into N1 by N2. So LLP is equal to LP minus M into N1 by N2, where LP is called as the self-inductance of primary winding, and M is the mutual inductance between the primary and the secondary winding, and this is N1 by N2. So this is a minus here. So this is LLP is called as the leakage inductance of the primary winding, and LLS is called as the leakage inductance of the secondary winding is equal to LS minus M into N2 by N1. So LS is called as the self-inductance of secondary winding minus M into N2 by N1. Then LLS dash. LLS is called as the leakage inductance of secondary winding referred to primary, which is basically LLS into N1 by N2 whole square, or basically here N1 by N2 whole square into, here you can substitute this LLS, this formula we are going to get. If you substitute this formula here, we are going to get finally LS minus N1 by N2 into M. So therefore this is a formula that you always have to remember, and LM is nothing but which is called as the mutual inductance referred to primary side is equal to M into N1 by N2. So M into N1 by N2. So listen carefully. LP is called as the self-inductance of primary winding, and LS is called as the self-inductance of the secondary winding, and M is called as the mutual inductance between the primary and the secondary windings. Then LLP is called as the leakage inductance of primary winding, and LS is called as the leakage inductance of secondary winding, and LM is called as the mutual inductance referred to the primary side, and LS dash is called as the leakage inductance of secondary winding referred to primary side. Always E1 by E2 is equal to N1 by N2, and LLP is equal to LP minus M into N1 by N2, and LS is equal to LS minus M into N2 by N1, and LLS dash is equal to LLS into N1 by N2 whole square. So if you substitute this formula here, you are going to get N1 by N2 whole square into LS minus N1 by N2 into M, and LM is equal to M into N1 by N2. So this is a very important formula that you always have to understand. So for a single phase transformer of E1 by E2, so E1 and E2 are the rated RMS values of the primary induced and the secondary induced. LP is called as the self-inductance of the primary winding, and LS is called as the self-inductance of the secondary winding, and M is called as the mutual inductance between the primary and the secondary winding. So LLP is called as the leakage inductance of primary winding, and LS is called as the leakage inductance of secondary winding, and LM is called as the mutual inductance referred to primary side, and LS dash is equal to leakage inductance of secondary winding referred to primary side. So A1 by A2 is equal to N1 by N2, LLP is equal to LP minus M into N1 by N2, LLS is equal to LS minus M into N2 by N1, and LLS dash is equal to basically LS into N1 by N2 whole square, or if we substitute this formula here, we are going to get N1 by N2 whole square into LS minus N1 by N2 into M, and LM is equal to M into N1 by N2. So these are the formulas that you always have to understand to solve this type of numericals. When transformer is operating at the maximum voltage regulation, we need series branch parameters. So when transformer is operating at the maximum voltage regulation, we need series branch parameters which can be figured out by short circuit data, test data, and now we can easily find the power factor of transformer. All this simply means that voltage regulation of transformer is maximum during the short circuit test. So listen carefully. When transformer is operating at the maximum voltage regulation, we need the series branch parameters which can be figured out by the short circuit test data, and now we can easily find the power factor of the transformer. All this simply means that regulation of transformer is maximum during the short circuit test. See, I have already told you one important point. During the short circuit test data, during the short circuit test you can figure out the series branch parameters, and also you need the series branch parameters to figure out the voltage regulation. So therefore I have already told you, so if by using the short circuit test we are going to get the series branch parameters, and the series branch parameters are useful for figuring out the voltage regulation of transformer. So therefore when the transformer is operating at the maximum voltage regulation, we need the series branch parameters which can be figured out by the short circuit test data, and now we can easily find the power factor of the transformer. All this simply means that the voltage regulation of transformer is maximum during the short circuit test. If nothing mentioned, then always draw positive phase sequence in the three-phase transformer connections. If nothing mentioned, then always draw the positive phase sequence in the three-phase transformer connection. See, in the three-phase transformer connections, if they are not mentioned regarding the what is the phase, then blindly go for the positive phase sequence in the clockwise direction. So if nothing mentioned, then always draw the positive phase sequence in the three-phase transformer connections. If they are not mentioned regarding the phase sequence, then blindly go for the positive phase sequence in the clockwise direction in a three-phase transformer. So if nothing mentioned, then always draw the positive phase sequence in the three-phase transformer connection. So in a star connection, I have already told you the line current is equal to line voltage, and the line current is always equal to line voltage, and the line voltage is equal to root 3 times of phase voltage, and the line voltage is going to lead the corresponding phase voltage by 30 degree in the positive phase sequence. Whereas in the negative phase sequence, the line current is equal to phase current, but the line voltage is going to lag the phase voltage by minus 30 degree. So therefore, the line voltage is going to lag the phase voltage by 30 degree. So you can add here minus 30. So the negative phase sequence. Similarly, in the delta connection, I have already told you the line voltage is equal to phase voltage, but the line current is equal to 2 times of phase current, and the line current is going to lag the phase current by 30 degree in case of positive phase sequence, and the line voltage is equal to phase voltage, and line current is equal to 2 times of phase current, and is going to lead the phase voltage by 30 degree in the negative phase sequence. So these are the important points that you always have to remember. Here in a star connection, the line current is always equal to phase current, whereas in the positive phase, the line voltage is going to lead the phase sequence by 30 degree. Whereas in the negative, it is a reverse. It is going to lag by 30 degree. So in the delta connection, we can say that always the line voltage is equal to phase voltage, but the line current is going to lag the phase current by 30 degree in the positive phase sequence, and the line current is going to lead the phase sequence by 30 degree in the negative phase sequence. So these are the things that you always have to remember. So in a star connection, the line voltage is equal to phase voltage, and the line current is equal to phase current, the line current is equal to phase current, and the line voltage is equal to root 3 times of phase voltage. In delta connection, the line voltage is equal to phase voltage, and the line current is equal to root 3 times of phase current. In DC generator, always the given data has output power and the terminal voltage. So always in the DC generator, whatever they are going to give in the question, basically these are the data corresponding to output power and the terminal voltage. So always in a DC generator, whatever the data they are going to specify, it is basically the terminal voltage and the output power. So always in a DC generator, whatever the data they are mentioning, basically they are called as the terminal voltage and the output power. So in DC generator, always the given data has the output power and the terminal voltage. So in a DC generator, whatever the data they are mentioning, these are basically the output voltage and the terminal power. So W is equal to integral of I into d lambda. So F is equal to Pw by dg, and C is equal to integration of lambda into di. So W is called as the mechanical energy in any moving part. So W is called as the mechanical energy in any moving part, and lambda is called as the flux linkage, and G is called as the air gap, and F is called as the mechanical force in any moving part, and C is called as the co-energy. So here W is equal to integration of I into d lambda, and F is equal to dW by dg, and C is equal to integration of lambda into di. It is reverse of this one. So W is equal to integration of I into d lambda, and C is equal to integration of lambda into di, and F is equal to dW by dg. So here W is basically implies that mechanical energy in any moving part, and the lambda is nothing but it is a flux linkage, and G is called as the air gap, and F is called as the mechanical force in any moving part, and the C is called as the co-energy. So W is equal to integration of I into d lambda, and C is equal to integration of lambda into di, and F is equal to dW by dg. So W is called as a mechanical energy in any moving part. So W is called as a mechanical energy in any moving part, and lambda is called as the flux linkage, and G is called as the air gap, and F is called as the mechanical force in any moving part, and C is called as the co-energy. So therefore W is equal to integration of I into d lambda, and co-energy is equal to integration of lambda into di, and F is equal to dw by dg. So these are important formulas that you always have to remember. So therefore W is called as the mechanical energy in any moving part, and lambda is called as the flux linkage, and G is called as the air gap, and F is called as the mechanical force in any moving part, and C is called as the co-energy. So same thing I have written, lambda is called as the flux linkage, and G is called as the air gap, and F is called as the mechanical force in any moving part, and C is called as the co-energy. So basically flux is equal to magnetic flux density into area, but here we are going to go for flux per pole means divided by pole. So flux is equal to flux per pole is equal to B into area per pole. Area is nothing but the cylindrical surface area, which is 2 pi r into L. So 2 pi r into L is called the surface area of a cylinder, 2 pi r into L by pole. So therefore flux is equal to, so basically flux is equal to magnetic flux density into area, but here we are going to choose for per pole. So flux per pole, so flux for phi is equal to B into area per pole. Area of the cylinder is equal to 2 pi r into L. So finally phi is equal to B into 2 pi r L by pole. So pi is called as the flux per pole, and B is called as the average flux density, and R is called as the radius of the armature core. So R is called as the radius of the armature core, and the L is called as the length of the armature core. So this is a very important formula. So pi is equal to B into area per pole. So B into area is nothing but 2 pi r L by pole. So therefore pi is called as the flux per pole, and B is called as the average flux density, and R is the radius of the armature core, and L is the length of the armature core. DC generator, the given current is always the output current. So in this generator, whatever the given current is always the output current. So in the question, I have already told you in the DC generator, whatever the data, they are going to basically mention about the terminal voltage, output power, and the output current, or simply load current. So listen carefully, in the DC generator, so whatever the data they are going to mention, they are called as the basic terminal voltage, output power, and the output current or load current. In DC motor, if we neglect the motor losses, means R is equal to 0, because suppose in the question, in the DC motor analysis, if they are going to mention that neglect the motor losses, means we have to assume R is equal to 0, because in the RA only there is a losses, so we have to assume R is equal to 0, by that the motor losses are 0. So therefore in the DC motor, if we neglect the motor losses, means this equation is going to basically going to imply that R is equal to 0. So in DC motor, if we neglect the motor losses, means RA is equal to 0. So therefore simply we can say in the DC motor, if you are going to neglect the motor losses, means RA is equal to 0. We already told you hysteresis loss is directly proportional to frequency, and a decurrent loss is directly proportional to square of the frequency whenever the V by F is a constant. So V by F is a constant means Vm is equal to constant, magnetic flux, the maximum flux density is a constant. So in a transformer, when maximum flux density is a constant. So now same principle we have to apply for DC machine also. Replace frequency by N, because N is proportional to frequency. So because N is proportional to frequency, because N is equal to 120 F by P. So N is proportional to frequency. So replace F by N, replace F by N. So we are going to get hysteresis loss is directly proportional to speed, and a decurrent loss is directly proportional to square of the speed. In DC machine, whenever the flux is a constant, because whenever the Vm is a constant, flux is also constant. So we can say flux is a constant. So therefore hysteresis loss is directly proportional to frequency, and a decurrent loss is directly proportional to square of the frequency whenever the transformer, whenever the magnetic flux, the maximum flux density is a constant, or simply we can say flux is a constant. Similarly in the DC machine also, N is nothing but N is equal to 120 F by P, so N is proportional to F, so replace F by N. So hysteresis loss is directly proportional to N, and a decurrent loss is directly proportional to square of the N. See, in a DC machine, in the armature there is a AC current. So whenever there is a AC current, definitely the iron losses are going to get produced. The summation of the hysteresis loss and the decurrent loss. So whenever the magnetic flux density is a constant, means flux is also constant. 100 volt, 70 ampere, 1000 rpm, DC series motor. All this data mean at rated or full load condition. 200 volt is applied as input, and it draws 70 ampere, and full load speed is 1000 rpm. So basically, let me a small example here. A 200 volt, 70 ampere, 1000 rpm DC series motor. This implies what? This basically implies that suppose if you give a terminal, if you give supply voltage of 200 volt, the current drawn is 70 ampere, and the full load speed, the full load slip, if you apply full load on this motor, the speed is nothing but 1000 rpm. This is what this data is going to give. So all this data mean at rated or full load condition, the 200 volt is applied as input and it draws a 70 ampere as input current, and full load speed is 1000 rpm. So this is the significance of this data. A 200 volt 70 ampere 1000 rpm DC series motor, basically this implies that so whenever you give a rated voltage of 200 volt input, the input current is 70 ampere, and then if you give full load, the speed is nothing but 1000 rpm. The speed at the full load is nothing but 1000 rpm by this motor. So 200 volt 70 ampere 1000 rpm DC series motor, all this data mean that at rated or full load condition, rated is also called as the full load condition, when 200 volt is applied as input and it draws a current of 70 ampere and the full load speed is 1000 rpm. See, P rotational is constant for any DC machine at any loading condition from no load to full load. And what I told you, the rotational losses is only function of speed. So from no load to full load, we are going to assume the speed is a constant. So therefore, the rotational losses is always constant. So therefore, simply we can say that the rotational losses is constant for any DC machine at any loading condition from no load to full load. So this is a very important point. So we can say that whatever the rotational losses means, I already told you, it is a summation of the core losses and also the mechanical losses. Rotational losses means it is a summation of the iron losses and also the mechanical losses. So for iron loss and mechanical loss are constant from no load to full load. So we can say that the rotational loss are also constant from full load, no load to full load. So rotational loss is constant for DC machine at any loading condition from no load to full load, because rotational losses is a summation of the iron loss and also rotational loss is a summation of the iron loss and also the mechanical loss. So mechanical loss means it is a summation of the friction and the windage losses. All these things I have already told you. So it is always constant irrespective of the loading from no load to full load. It is always constant. So therefore we can say that the rotational loss is constant for any DC machine at any loading condition from no load to full load. So Tm is called as the plugging torque and TL is called as the load torque and Tb is called as the braking torque. So always braking torque is a summation of the load torque and also the plugging torque. So therefore braking torque is always a summation of the load torque and the plugging torque. So therefore braking torque is always a summation of the load torque and also the motor torque or the plugging torque. So Tm is also called as a plugging torque or motor torque. So therefore whatever the braking torque is always the summation of the load torque and also the motor torque or the plugging torque. So Tb is called as a braking torque and TL is called as a load torque and Tm is called as a plugging torque or the motor torque. So the braking torque is always a summation of the load torque and also the plugging torque or the motoring torque. So braking torque is a summation of the load torque and the motoring torque or the plugging torque. So Tb is equal to TL plus Tm. So Tb is called as a braking torque and TL is called as a load torque and Tm is called as a motoring torque or the plugging torque. So always we can say that basically we are going to get initial letter as a B. So we have to go for the addition of the remaining two things, L and M. So in the English alphabetical orders, B you are going to get first. So taking this one as earlier, and the remaining two things you have to add, L and M, you have to add them. So therefore Tb is equal to TL plus Tm. Tb is called as the braking torque and TL is called as the load torque and Tm is called as the motor torque or the plugging torque. Speed of the rotating magnetic field is equal to 120 F by P with respect to where the supply is given, stator or rotor. It's a very important point. See, speed of the rotating magnetic field is equal to 120 F by P with respect to where the supply is given, either on the stator or either on the rotor. See, this is a very important point. This is the thing that you always have to remember. The speed of the rotating magnetic field is equal to 120 F by P with respect to where the supply is given, either on the stator or either on the rotor. So this is a very important point. If you give a supply to the stator, then definitely stator is a stationary. So therefore, let me assume it is going to rotate in the clockwise direction. So therefore, the speed of the rotating magnetic field is equal to 120 F by P with respect to where the supply is given, either stator or the rotor. Suppose if you given the rotor, then the speed of the rotating magnetic field with respect to rotor is 120 F by P. So this is a very important point. So always the speed of the rotating magnetic field is equal to 120 F by P with respect to where the supply is given, either on the stator or either on the stator or either on the rotor. The speed of the rotating magnetic field is equal to 120 F by P with respect to where the supply is given, either on the stator or either on the rotor. So this is a very important point. So if you give a supply to stator, then definitely we can say that the speed of the rotating magnetic field with respect to stator. Suppose if you give supply on rotor, then the speed of the magnetic field with respect to rotor is 120 F by P. So therefore, simply we can say that the speed of the rotating magnetic field is equal to 120 m by p with respect to where the supply is given, either on the stator or either on the rotor. The speed of the one magnetic field with respect to other magnetic field is always zero. The speed of the one RMF rotating magnetic field with respect to other rotating magnetic field is always zero. Then only shy torque is going to get produced. And all I told you, they should always rotate in the same direction with the same speed. Then all I told you that two rotating RMFs should be always rotating in the same direction with the same speed. Then only we can say their relative speed difference is equal to zero. Then only the shy torque is going to get always obtained. So the speed of one rotating magnetic field with respect to other rotating magnetic field is always zero. Then only a steady torque is going to get produced. So very important point. The speed of one of the rotating magnetic field with respect to other rotating magnetic field is always zero. Then only steady torque is going to get produced. It means that the two rotating magnetic fields must rotate in the same direction with the same speed. Then only we can say their relative speed difference is zero. Then only a shy torque is going to get produced. Then only a shy torque is going to get produced. So we can say that the speed of one rotating magnetic field with respect to other rotating magnetic field is always zero. Then only the shy torque is going to get produced. Here, speed of A with respect to B is equal to speed of A with respect to G minus speed of B with respect to G. All these are the direction sensitive. So all these are the vector equations. So these are direction sensitives. If you take one direction as a positive, the other things will be negative. So if you take one direction as a positive, if anything which is opposite to that direction is called as the negative, and the things which are in the direction are called as a positive. So listen carefully. See, let me assume one direction as a positive. If any vectors which are rotating in the opposite is called as the negative, and any vectors which is in the same direction as the assumed, it is said to be positive. So this equation is basically a speed. So this equation is said to be a sign sensitive equation. So therefore, NAB is equal to NA with respect to ground minus NB with respect to ground. All these are the direction sensitive, or we can say sign sensitive equations. Speed of A with respect to B is equal to speed of A with respect to ground minus speed of B with respect to ground. These are vector quantities, means these are direction sensitive quantities. So we have to assume one direction as a positive, and if any vectors which is in the same direction is said to be positive, and if any vector which are opposite to this direction is said to be negative. So in induction motor, I have already told you S is the slip is equal to ns bar minus nr bar by ns bar. So we can see that suppose if the two vectors are in the same direction, if these two vectors are in the same direction, and this is also positive and this is also positive, so replace these two positive values, we are going to get ns minus nr by ns. But if they are opposite, if they are basically opposite, then what we have to do? Let me assume this direction, this clockwise is positive, ns is a positive but nr is a negative. So you have to replace nr by minus nr, because these are the direction sensitive. So replace here, we are going to get ns plus nr by ns. So replace ns by plus ns and nr by minus ns, you are going to get this equation. So therefore, so whenever in the same direction, whenever ns and nr in the same direction, we are going to get slip is equal to ns minus nr by ns, and whenever they are opposite direction, then the slip is equal to ns plus nr by ns, because this is the relative speed. This is the relative speed between the two speeds. Here it is a negative, here it is a positive. Then f dash is equal to s into f. Always you have to take the magnitude of this s. Always you have to take the positive value only you have to take. So f dash is equal to s into f. Always you have to take the positive value of the s. It is called as the slip frequency. So this is called as the rotor frequency or the slip frequency, and f is called as applied frequency, and s is called as the slip. So we can say slip terms of frequency is also called as the slip frequency in general. So therefore, or rotor frequency or the frequency of the induced EMF or induced currents. So f dash is equal to s into f. Always you have to take the absolute value of the s only. So in induction motor, we will see different equations. The torque is equal to, we are going to get 3 by omega s into Vt square into R2 by s into R2 by s whole square plus x2 square. I have already told you one important formula which is very simple. I have already told you which is very simple formula, which is called as basically here 180 by, so 180 by 2 pi ns, or simply we can also call this as basically here 3 by omega s, because 2 omega s, I think about 2 by ns by 60. If 60 goes upward, we are going to get 180 by 2 pi ns. So simply we can write 3 by omega s or 3 by omega s or 180 by 2 by ns. Here I have already told you s into E2 square R2 by R2 square plus s x2 square. So let me divide by s or numerator on the denominator. Then we are going to get in this format, which is, so here let me take a small example here. I have already told you this is s into E2 square R2 by R2 square plus s x2 square. if I take here S square as a common here, so if I take S square as a common here, then definitely R2 by S whole square plus X2 square. So therefore, if I take here S square as a common, definitely we have to do here R2 by S whole square plus X2 square. Again there is a S here there is a S square. So you are going to get S again. S by S square is nothing but S. So this is going to go here. So therefore, this is the equation that we are going to get. So whatever the formula that I have already told you, just take S square common in the denominator, and this is S square and this is S. It is going to cancel. So we are going to get this equation. So V2 is nothing but E2, which is the per phase voltage induced in the rotor. So you can write either that format or either this format, and you are going to get the same result. So this is the equation when the stator impedance is neglected. So this is the equation that you are going to get whenever the stator impedance is neglected. Now we have to modify if you want to consider the stator impedance. So whenever the stator impedance is considered, just you have to add here R equivalent, and here you have to add the X equivalent, and remaining everything is same. Just add here R equivalent and just add the X equivalent. So whenever the stator impedance is considered, so this is the equation of the torque. Just add the R equivalent and X equivalent. So this is the equation that you are going to get when you consider the stator impedance is considered. So this is the equation that you are going to get whenever the stator impedance is considered. Then what is the power developed? Power developed is equal to torque into omega r, because here the rotor is going to rotate with the speed of nr. So therefore this is omega r, which is 2 pi nr by 60. So power developed is equal to T into omega r, because it is the omega is nothing but 2 by nr by 60. Now power factor formula I have already told you, which is R2 by under root over R2 square plus SX2 square. These things I have already told you. So power factor is equal to R2 by under root over R2 square plus X2 square, SX2 square. So R2 by under root over R2 square plus SX2 square. So here let me take here. So if I take the S square common here, we are going to get basically then R2 by S whole square plus X2 square. If this S square comes outside the root, then we are going to get S. Again you are going to get, if it goes upward, you are going to get in this format. So you can write either in this format or R2 by under root over R2 square plus SX2 square. Both are same. You can write either in this format which I have told, or either in this format, and now you are going to get the same result. So slip at maximum torque is equal to R2 by X2 when the stator impedance is neglected. Then if you consider the stator impedance, then you have to do like this: R2 by under root over R equivalent square plus X equivalent plus X2 whole square. So this is the thing that you always have to do this one. So it is going to modify by under root over R equivalent square plus X equivalent plus X2 whole square. So like this you are going to get whenever you consider this equation. So therefore whenever you consider the stator impedance, it is going to become R2 by under root over R equivalent square plus X equivalent plus X2 whole square. So this is the equation that you are going to get. The slip you are going to get whenever the stator impedance is considered, which is R2 by under root over R equivalent square plus X equivalent plus X2 whole square. And the maximum torque, I have already told you, the expression of the maximum torque is equal to 180 by 2 pi ns into E2 square by 2 into X2. Here E2 is nothing but V2. I am going to write E2 as V2 in this case. So therefore omega ns is nothing but 2 pi ns by 60. So if you take the 60 upward, we are going to get 180. So we can write either in this format or that format, which is 180 by 2 pi ns into V2 square by 2x2 or 3 by omega s into V2 square by 2x2. Anyway, it is same. All the things are always same. So listen carefully. This SM is somewhat different. This is not the thing which you have learned here. This is the different SM. This SM is different, which is the slip at the maximum mechanical power. So this is basically, this SM is nothing but, the green color SM is nothing but, which is the slip at the maximum mechanical power. So this is basically the slip at the maximum mechanical power is equal to R2 by R2 plus X2 when the stator impedance is neglected, or by it is R2 by R2 plus under root over R equivalent square plus X equivalent plus X2 whole square whenever the stator impedance is considered. So in the previous case we have learned the slip at maximum torque is nothing but R2 by X2, and here R2 by under root over R equivalent square plus X equivalent plus X2 whole square. Just you have to add R2 in the denominator for both the equations. So in the previous equation we have learned this is not there, here this is not there. Just you have to add the R2 in the denominator for both these two things. Then we are going to get like this. So therefore simply we can say that we have to add the R2 for the denominator for both the things. So then we are going to get this one. So this SM is going to represent the slip at the maximum torque, and this is the slip at the maximum mechanical power. Slip at the maximum mechanical power. So whatever these two equations, just add here R2 here and R2 add the R2 here. So you are going to get these equations. So just add the R2 here and also add the R2 here. So you are going to get these equations. This is the equation when the stator impedance is neglected, and this is the equation when the stator impedance are considered. This is basically the slip at the maximum mechanical power, and this is the slip at the maximum torque. The air gap power is nothing but this is called as the PG is called as the air gap power, or simply rotor input or stator output, which is basically the rotor copper loss by slip. Because the rotor copper loss is equal to slip times the rotor input. The rotor input is equal to rotor copper loss by S. As it's a three phase, so you have to get 3 times of I2 square into R2. So because it's a three phase, so 3 into I2 square into R2 by slip is S. So you have to just take the magnitude of the current. So you have to take only the magnitude of the current, which is R2 by S here. So this is the equation that you are going to get. Then what is the mechanical power developed? Mechanical power developed is nothing but rotor input minus copper loss, the rotor copper loss. Then you are going to get, which is simply here rotor input into 1 minus S. So this is the rotor input, which is Vg, 3 into mod of I2 whole square into R2 by S into 1 minus S. So NR is called as the NR is equal to NS into 1 minus S. This is in terms of the RPM. NR is called as the rotor speed. NS is the speed of the rotating magnetic field in terms of RPM, and S is the slip. So you can write in the same format. So just do the multiplication by 2 pi by 60 on the both sides. We are going to get omega R is equal to omega S into 1 minus S. This is in terms of the radians per second. So if you multiply by 2 pi by 60 on both sides, we are going to get omega R is equal to omega S into 1 minus S. So V2 is called as the rotor per phase voltage. See, we can use V2 or E2, anything, both are same. So we can use V2 or E2, both are same, just called the rotor per phase voltage, which is the rotor induced per phase voltage, induced rotor per phase voltage, and R2 is called the rotor per phase resistance, and X2 is called as the rotor per phase reactance at the stand chain. So rotor per phase reactance at the stand chain, and SF is called as the slip at the maximum torque, and TMAX is called as the maximum torque, and this green SM, the green SM is called as the slip at the maximum mechanical power, and PG is called as the air gap power of the rotor input or stator output. So PM is called as the mechanical power developed, and P developed is called as the mechanical power developed. So we can go for PM or P developed, both are same, which is mechanical power developed or mechanical power developed. You can use any of the notation, both are same. So P developed is nothing but PM, which is equal to mechanical power developed. So therefore mechanical power developed is equal to T into omega. Just now we have seen. So P developed, see, whenever there is no rotational loss, whenever there is no friction, or we can say whenever there is no friction and windage losses, then power developed is equal power, mechanical power output is nothing but just power developed. So therefore here mechanical power developed is nothing but power developed, or you can use the any of the, see, basically shaft power is nothing but it is a difference of the mechanical power developed minus friction and windage losses. So always the shaft power is always lesser than the mechanical power developed. So you can use the any of the equation. So always the power developed is nothing but mechanical power developed, or you can use the notation PM or P developed, both are same. So you can use the notation PM or P developed, both are always same. Just mechanical power developed or developed mechanical power, anything which is same. So it is nothing but, so we can write basically this T into omega, and it's also T into omega, both are same. Power factor PF is called as a power factor. So in induction motor, if the load torque is greater than maximum torque produced by induction motor, this phenomenon is called as the stalling. If load torque is greater than the maximum torque produced by induction motor, this phenomenon is called as the stalling. So what happens during the stalling condition? See, basically whenever the load torque demand is higher than the maximum torque produced by the induction motor, then that motor will never rotate, because it cannot produce that much amount of torque needed by the rotor, so by the load. So because the load torque is very high when compared to maximum torque produced by the motor, so therefore it cannot rotate it. So it is in the standstill condition. So NR is equal to always 0, which is called as the stalling condition. So whenever the load torque demand is greater than the maximum torque developed by the induction motor, then we can say it is stayed to the stalling condition. So it will never rotate. The motor will never rotate. It will be in the standstill condition for all the time. So if the load torque is greater than the maximum torque produced by induction motor, this phenomenon is called as the stalling. So stalling speed is defined as the speed of the rotor at maximum torque. So stalling speed is defined as the speed of the rotor at the maximum torque. So stalling speed is defined as the speed of the rotor at the maximum torque. So these are the important points that you always have to remember. The stalling speed is defined as the speed of the rotor at the maximum torque. See, I've already told you from 0 to SM. So whenever the slip is varying from 0 to SM, it is said to be a low slip region. In a low slip region, I've already told you S into X2 is always lesser than the S into X2 whole square is always lesser than the R2 square. So we have to neglect the S into X2 whole square. So finally we are going to get torque is directly proportional to S into E2 square by R2 into F. I have already told you this important point. See, V2 is nothing but E2. You can go for any other thing. The same rotation. So torque is directly proportional to S into V2 square by R2 into here also there is a F here. So here you have to take care F also. But let me also frequency the constant, so you can write either in this format. So whenever the slip increases, then the torque is increases. So these both are directly proportional and it is said to be a stable region. I will explain why it is said to be a stable region. Whereas whenever the slip is varying from SM to 1, it is called as the high slip region or it is unstable region. So I have already told you in the high slip region, S into X2 whole square is always greater than the R2 square. So we have to neglect the R2 square. So if you do this one, we are going to get finally torque is directly proportional to R2 by S. As you can see clearly, as S increases, the torque is going to get decreased. So both are inversely proportional. So whenever the slip increases, the torque will reduce. So this is called as the unstable region. These things I have already told you. So whenever in the stable region, as the slip increases, torque increases. Whereas in the unstable region, as the slip increases, the torque will decreases. These things I have already told you. Then here I have already told you the ratio T by T max is equal to 2 into S into Sm by Sm square plus S square. These things I have already told you. T by T max is equal to 2 into S into Sm by S square plus Sm square. The T is called as the any torque at corresponding slip is equal to S. And T max is called as the maximum torque at corresponding slip is equal to Sm. These things I have already told you. T by T max is equal to 2 into S into Sm by S square plus Sm square. The T is called as the any torque of induction motor at a corresponding slip of S. And T max is called as the maximum torque produced by the induction motor at a slip Sm. So you can take any torque at any slip. You can take either the starting torque, either you can take the any full load torque, but you have to take the corresponding slip also. Starting torque means you have to take the starting slip. If you take full load torque means you have to take the corresponding full load slip. If you take any other torque, then you have to take that corresponding slip that you have to take. So therefore, T by T max is equal to 2 into S into Sm by S square plus Sm square. So T is called as the any torque at the corresponding slip is equal to S, and T max is called as the maximum torque at the corresponding slip is equal to Sm. So I have already told you the developed power. The developed power is nothing but output power plus mechanical losses power. These things I have already told you always. So whatever the mechanical power developed is equal to shaft power or output power plus mechanical power. So output power is also called as the shaft power plus mechanical power, means the mechanical power loss. So therefore, because of the friction and the windage losses. So whatever the power developed means I have already told you, which is 1 minus S into rotor air gap power. So therefore rotor, or you can say air gap power. So 1 minus S into air gap power. So P developed is called as a mechanical power developed, which is called as the mechanical power developed. You can use the symbol PM or P developed, both are same. Is equal to output power plus the mechanical power loss. It is also called as the friction and the windage losses. So output power is also called as the shaft power. So shaft power plus mechanical loss power is equal to, I have already told you, the power developed is called T into omega R. Just now I have told you. So T into W omega R, because at the power developed, the rotor is rotating at a speed of omega R. So it is T into omega R. So omega R is nothing but T into omega S into 1 minus S. Omega R is equal to omega S into 1 minus S. So this is the equation that you are going to get. So always remember, which is power developed, the mechanical power developed is equal to output power plus the mechanical power loss. So the output power is also called as shaft power plus mechanical power developed. The mechanical power developed is nothing but T into omega R. So T into omega is nothing but omega S into 1 minus S. These things I have already told you. See, always by default in induction motor, the shaft power will be always given. See, always in induction motor, whatever the data they are going to give, it is always going to mention about the output power only. So therefore, in the induction machine, in the induction motor, whatever the data they are going to mention, by default, it is always the shaft power or the output power. So always by default induction motor, whatever the data they are going to mention, it is always said to be output power or the shaft power. So always by default in induction motor, whatever the data that they are going to mention, it is all about the shaft power or the output power will be given. See, this is a very important point. See, d by dn of load torque is greater than d by dn of electric torque. So electromagnetic torque. So this is the at the operating point. At the operating point, intersection of the TL and P curves. Then that operating is said to be a stable point. So therefore, TL is called as the load torque and T is called as the electromagnetic torque. So this is a very important point. The rate of change of load torque with respect to speed must be greater than the rate of change of electromagnetic torque with respect to speed. If this is the case at the operating point is basically intersection of the load torque and the load torque and the electromagnetic torques. Then only we can say that that corresponding point is said to be a stable point. Then that operating point is said to be a stable point. It's a very important point. Listen carefully. Whenever the derivative of the load torque with respect to speed is greater than the derivative of the electromagnetic torque with respect to speed. If this is the case, this is the point at the operating point you have to do. Operating point means it is the intersection of the load torque and the electromagnetic torque curves. Then that point is said to be always stable point. So TL is called as the load torque and T is called as the electromagnetic torque. So therefore, the rate of change of load torque should be always greater than the rate of change of load torque with respect to speed should be always greater than the rate of change of electromagnetic torque with respect to speed at the operating point. The operating point is basically the intersection of the load torque curve and the electromagnetic torque curve. So at that point, whenever this condition is satisfied, that point is called as the operating point is called as a stable point, and TL is called as a load torque and T is called as a electromagnetic torque. So whenever the rate of change of load torque with respect to speed is greater than the rate of change of electromagnetic torque with respect to speed, then we can say at the operating point is basically the intersection of the load torque curve and the electromagnetic torque. If this is the case, that operating point is said to be a stable point, and TL is called as the load torque and T is called as electromagnetic torque. So now other important concept is called as the no load test on the three-phase induction motor. The another test is called as the no load test on a three-phase induction motor. So I already told you the performing the no load test on a three-phase induction motor is similar to performing the open circuit test on a single phase transformer. So now here we are going to get a no load voltage of, with the help of voltmeter we are going to get voltage V0, current I0 and torque P0. So V0 is the no load rated voltage that we have to give, and I0 is called as the no load input current we are going to get, and P0 is something that we are going to get the power which is input at this three-phase induction motor at the no load condition. This much amount of power is consumed by the three-phase induction motor at the no load condition, and the current drawn is I0, and the voltage, the rated no load voltage that we are going to give is V0. I already told you the armature resistance. You can write RA or RS, anything is same. RS is called as the armature resistance of the winding is nothing but the AC is equal to always the armature resistance DC into, we have to do a factor of, S is called as a factor. So S is called as a factor. So this factor we have to multiply. S is called as a skin effect factor. It is basically, so the question they are going to give you, this is the DC resistance into skin factor that we have to multiply. S is called as the skin effect factor. Normally it is nearly equal to 1.5. So normally it is nearly equal to 1.5. So the resistance, the armature winding resistance, you can write RS or RA, anything which is same. So RA or RS is same. So therefore it is always DC multiplied by skin factor. So RA AC is equal to RA DC into skin factor. And what is the no load impedance? The no load, at the no load condition, the impedance is nothing but just to the for the per phase you have to draw the per phase diagram. At the per phase I have already told you at no load the S is equal to, the slip is equal to nothing but, which is very simple, Ns minus Nr by Ns. At no load Nr is nearly equal to Ns. So slip is equal to, we can say that it is 1. So therefore as a slip is equal to 1 in the equivalent circuit diagram I have already told you there is a R2 dash X2 dash and here R dash into 1 by S minus 1. Then we are going to get like this, as S is equal to 1, 1 by 1 minus 1 is nothing but 0. Basically at no load condition Ns is equal to Nr. So slip is equal to 0. So 1 by S minus 1 is nothing but 1 by 0 minus 1 is equal to infinity. So it is open circuit. So only shunt branch is going to get present. So which is ZNL is equal to V phase by I phase. And what is the RNL? RNL is equal to, we have to go for the per phase power by I phase whole square, because RNL is nothing but per phase power by I phase whole square, which is equal to, we have to take on the per phase, and the 3 phase we have to divide by 3. So P0 by 3 by I phase whole square. Then what is XNL is equal to under root of ZNL whole square minus RNL whole square. So we can say that we know the value of ZNL, which is V phase by I phase. These are basically line voltage. It is a line voltage. So we have to go for the, this is basically line voltage. So we have to divide by root 3 to get the phase voltage, which is V0 by root 3. So V phase is nothing but which is V0 by root 3. By I phase we have to do. As let me assume the station is connected in the star connection. So definitely the line current is equal to phase current, which is equal to I0. So we can substitute here I phase is equal to I0 here. So RNL is equal to power per phase by I phase whole square, which is P0 by 3 by I phase whole square. Then XNL is equal to under root over ZNL whole square minus RNL whole square. I have already told you one important point. Whatever the, at no load condition, whatever the input power, it is basically, see I have already, it is in terms of losses, because output we are not going to do any useful power. So output is equal to 0. So now whatever the input power should be going to losses. The losses are nothing but, I have already told you, the stator core loss, and the stator copper loss, and the rotor copper loss, and also the rotor core loss is neglected. So we are going to neglect that part. And there is one is called as the mechanical power, or we can say mechanical power loss or friction and windage losses. So now we have only 4 components. One is called as the stator copper loss, stator core loss, rotor copper loss, and the mechanical losses. I have already told you a very important point, which is called as the iron loss, and also the mechanical loss is also called as the summation of the iron loss and the mechanical loss is called as the rotational losses. Then we are going to get very simple, which is finally whatever the input is equal to losses is equal to rotational losses plus stator copper loss plus rotor copper loss. So these are the things that you are going to get. Then what is the rotational losses? Input power minus, this is called as the stator copper loss. So this is called as the stator copper loss. So we have to neglect even rotor copper loss. So rotor copper loss also we are going to neglect, because I have already told you whenever the slip is equal to 0, then what is the rotor copper loss? Rotor copper loss is equal to slip times the rotor input. As slip itself is equal to 0, the rotor copper loss is also 0. So finally we can say whatever the input power is equal to losses, only losses that we have. Now finally the losses that we have is called as the stator core loss, stator copper loss, and also the mechanical loss. But I have already told you stator core loss plus mechanical loss is called as rotational losses. So finally we can say whatever the losses is equal to the rotational losses plus stator copper loss. So then we can say the input power is equal to rotational losses plus stator copper loss. But if you want rotational losses, input power minus stator copper loss, which is 3 into I phase whole square into RASAC. So therefore you have to go for the AC part here. So input power minus 3 times of I phase whole square into RS into AC. So I phase whole square into RS AC. This is called the armature resistance. AC value we have to take the armature resistance, because in the windings it is a AC current. So we have to take the corresponding AC resistance only we have to take. So RS is always equal to RA. You can write here RA, armature resistance RA or RS. You can take anything. RS is called stator resistance or armature resistance. You can do anything. So RA is called as RS or RA. Then I have already told you input power is nothing but rotational losses plus stator copper loss. So therefore rotational losses is equal to input power minus stator copper loss. Stator copper loss is a 3 phase, so 3 into I phase whole square into RS AC. So like this, that you always have to remember the concept in this manner. So now listen carefully. S is called as the skin effect factor and R is called as the stator per phase resistance, or we can say basically armature coil resistance. You can call anything. So R is called as the stator per phase resistance. So R is called as the stator per phase resistance or armature coil present on the stator. You can call anything. So basically R is called as the stator resistance per phase. So I have already told you here RL is nothing but RC. It is nothing but RC. RC is called as the core loss component of the resistance. It is RC because it is a shunt branch parameter, RC and XM. So only RC is going to consume the power but not the XM. So RC is nothing but RL is equal to power per phase by I phase whole square, which is P1 by 3 by I phase. For star connection, I phase is equal to IL, which is equal to here in this case I0. So therefore RC is equal to RL is equal to power per single phase diagram by I phase whole square is equal to P0 by 3 by I phase whole square. So like this we have to get the RC component. So now we have to perform the logged rotor test on a 3-phase induction motor. I have already told you the short circuit test on a transformer is equal to the blocked rotor test on a 3-phase induction motor. So now we have to block the rotor. So whenever you block the rotor, NR is equal to 0, so slip is equal to 1. Then whatever so we have to give the rated voltage. So input voltage is very less. A small amount of voltage you are going to get a rated input current. So V1, I1 and P1. So power constant is nothing but P1. And the voltage V1 we are going to give. The current is rated current I1. And P1 is the power which is consumed by this 3-phase induction motor at this block rotor test. And I already told you here, as in the equivalent circuit diagram, there is R dash into 1 by S minus 1 as S is equal to 1 in this case. As S is equal to 1, then 1 by S minus 1 is nothing but 1 minus 1 is equal to 0. So we have to do the short circuit there. So shunt branch we have to neglect. So only series parameters are going to present, which is R2 dash and the X2 dash. And here it is R dash, here it is R2 dash, X2 dash, and here R dash into 1 by S minus 1. It is going to become 0 because R dash into 1 by S minus 1 is nothing but 0. So you are going to get only R2 dash and the X2 dash you are going to remain. Then what is ZBR is nothing but V phase by I phase. It is always ZBR is equal per phase. We have to take the per phase diagram because whatever the equivalent circuit is a per phase diagram. So V phase by I phase. Then what is RBR is nothing but power per phase by I phase whole square. Power per phase is nothing but it is a 3-phase power. So you have to divide by 3. So P1 by 3 by I phase square. Then XBR is nothing but root of ZBR whole square minus RBR whole square. So now equivalent circuit parameters. The equivalent. So from the no-load test we are going to figure out the shunt branch parameters, and from the block rotor test we are going to find the series branch parameters. So now we will see each and everything. So listen carefully. X1 is always equal to X2 is equal to XBR by 2. So whatever the X1 and X2 both are equal to XBR by 2. XBR by 2. So X1 is equal to X2 is equal to XBR by 2, and Xm is always equal to XNL minus X1. XNL minus X1. XNL value just now we have solved from the no-load test. So we have to multiply by, we have to minus by X1. And R1 is nothing but RSAC. And R2 is equal to RBR minus R1 into Xm plus X2 by Xm whole square. So this is the thing that you are going to get. So these are the equations by which we are going to get the shunt branch parameters and the series branch parameters. So like this we can easily get the values of each and every thing. I already told you RC is nothing but RC is equal to RNL. So RC is always equal to RNL. Just now I told you. So RC, the core loss component resistance, is equal to RNL. So X1 is equal to X2 is equal to XBR by 2. Then XM is the XM is nothing but XNL minus X1, and R1 is equal to RSAC, and R2 is equal to RBR minus R1 into Xm plus X2 by Xm whole square. Where X1 is called as the leakage reactance of the stator, X2 is called as the leakage reactance of the rotor, and Xm is called as the magnetizing reactance, and R1 is called as the stator resistance, and R2 is called as the rotor resistance. Then RC is called as the basically the core loss component resistance. RC is equal to RNL. So like this that you have to always remember. So therefore X1 is equal to X2 is equal to XBR by 2, Xm is equal to XNL minus X1, and Xm is nothing but XNL minus X1, and R1 is equal to RCSA, R2 is equal to RBR minus R1 into Xm plus X2 by Xm whole square. X1 is called as the leakage reactance of the stator, X2 is called as the leakage reactance of the rotor, Xm is called as the magnetizing reactance, and R1 is called as the stator resistance, and R2 is called as the rotor resistance. So like this we are going to get, and RC is equal to RNL, RC is called as the rotor, the core loss component of the resistance, core loss component of resistance. Like this we have to always remember. So core loss resistance, RC is called as the core loss resistance. So starting methods of induction motor, I have already told you why we have to use the starting methods, because during the starting I have already told you there is a sudden dip of voltage and a sudden dip of current. So because of this reason only we have to reduce this one to a small values. So by using that, so basically the starting methods of induction motors, because why we are going to use is basically at no load condition, whatever the rotor induced voltage and the rotor currents are very higher values. But when it is running, you can say these values are very less because of the slip factor. So there is a sudden dip of voltage and sudden dip of current. So this is a very dangerous for the big reading machines. But for small reading machines it is not, it's okay. But for high reading machines it is very difficult. So by using the starting methods of induction motor, we are going to reduce this one. So therefore the methods are the direct online starting. So whatever the current is called starting current or starting torque, and the star delta starter, and the auto transformer, and these are the methods. In dual method of starting current is also called as the short circuit current. So in the dual method, starting current is also called as the short circuit current. So in the dual method, starting current is also called as the short circuit current. So you can go for the any of the name. So these are the three methods by which we are going to start the induction motor, because at the starting the induced EMF in the rotor and the induced current in the rotor are very high. But if you are going for the running condition, the induced EMF and the current are very less. So there is a sudden dip of voltage and current in the rotor. So this is very dangerous for the high rating machines, but it is okay for the small rating machines. So because of this is only we are going to use the starting methods of induction motor. So these are the three methods which is called direct online starting, in starting current and a starting torque. Starting current is also called as the short circuit current in the direct online starting, and it is called as the star delta starter, and this is auto transformer starter. So by using the starting methods, we are going to decrease the starting currents, but we are going to increase the starting torque. So this is an important point that you always have to remember. So now you will see the different formulas. In dual method, starting current is also called as the short circuit current. So therefore now in the star delta starter, I have already told you, in the star delta starter, the starting current is equal to 1 by 3 times the short circuit current, and the starting torque is equal to 1 by 3 times the, see, the starting current in the star delta is equal to 1 by 3 times the starting current of DOL. Similarly, the starting torque of star delta starter is equal to 1 by 3 times the starting torque of the DOL. So this is a very important point that you always have to remember, which is the starting current of the star delta starter is equal to 1 by 3 times the starting current of DOL, and the starting torque of star delta starter is equal to 1 by 3 times the starting torque of the DOL. So now the starting torque of the star delta starter is equal to 1 by 3 times the starting current of DOL. Similarly, the starting torque of star delta starter is equal to 1 by 3 times the starting torque of the DOL. So here starting current of DOL is also called as ISC, and the starting torque of DOL is also called as the TSC. So these are the things that I have replaced. So starting current in the DOL is also called as the short circuit current. So listen carefully. In the direct online starting, the stator of the induction motor is always connected in the delta fashion. Whereas in the star delta starter, initially for the initial operation, the stator winding is connected in the star fashion, and later at the running condition we are going to convert into delta fashion. It's a very important point. And the starting torque is always directly proportional to phase voltage over sphere. And here basically these currents are going to simplify the line currents. These currents are basically the starting currents of star delta and starting currents of DOL are basically they are going to represent the line currents. They are going to represent the line currents. So now we'll discuss the another thing which is called as the auto transformer starter. So always the tapping. So we are going to take the tappings of the auto transformer. So we have to take the numerical value. So x is going to lie between 0 to 1. So then starting current is equal to x square times the ISC, and TST is equal to x square times the TSC. Basically it means that whatever the starting current in the auto transformer is x square times the starting current of DOL, and the starting torque through auto transformer is equal to x square times the starting current of DOL. So it is going to mean like that. So therefore simply we can say that whatever the starting current because of the auto transformer is equal to x square times the starting current of DOL, and the starting torque of the auto transformer is equal to x square times the starting current of DOL. So therefore now I have already told you the starting torque by full load torque is equal to, the starting torque by full load torque is equal to starting current by full load current whole square into ISF SFL. These things I have already told you. But now the starting current is nothing but just replace the starting current by x times of starting current. So we are going to take outside x here x square, because whatever the starting current is x square times the ISC. These things I have already told you. The starting current of auto transformer is equal to x square times the starting current of DOL, and the starting torque of auto transformer is equal to x square times the starting torque of DOL. I have already told you this formula, which is the starting torque by full load torque is equal to starting current by full load current whole square into slip at full load by slip at starting torque is at the slip at starting torque is equal to 1. So we are going to get this formula. But now this is in the auto transformer. In the auto transformer, what is the starting current by auto transformer, which is x square times the starting current of DOL. So we have to replace this one value by x square into, this is nothing but ISC. So x square we are going to take it outside. They are going to get x square times the ISC by IFL whole square into SFL. So this is the equation that you are going to get. This ISC is called as the starting current because of the DOL connection. So this is the thing that you always have to remember this one. So this IST is nothing but starting current because of the auto transformer. It is equal to X square times the starting current because of DOL. So this is nothing but ISC. So now you have to replace a small correction here. Here starting current to auto transformer is equal to X times the starting current because of the DOL. So this is not X square. This is basically X. So whatever the starting current through auto transformer is equal to starting current of DOL into X. But here in the torque it is X square. So now we have to replace whatever the starting current through auto transformer is equal to X times the starting current of dual. So if you take X outside, we are going to get X square. So this is a small correction. This is not X square. This is X. So starting current through auto transformer is equal to X times the starting current through dual. Similarly, the starting torque through auto transformer is equal to X square times the starting torque because of dual. And what I told you the general expression. So the starting torque by the full load torque is equal to starting current by full load current whole square into slip-height full load by slip-height starting. As slip-height starting is equal to 1, we are going to get this equation. But now we are going to apply this for the auto transformer. Then the starting current through auto transformer is equal to X times the starting current of DOL. So X we are going to take it outside. We are going to X into the starting current of DOL is nothing but short circuit current. So ISC. So we are going to get this equation. We are going to get for this auto transformer. So a small correction. This is not X square. This is X. Whereas for starting torque through auto transformer is equal to X times the starting torque to the DOL. So this is the important concept that you always have to remember. So this is not X square. This is actually X. So in the nameplate details of induction motor, the given speed is rated speed at full load. I have already told you in the nameplate details of the induction motor, whatever the speed they are going to give you, it is the rated speed, or we can say full load speed. So if you keep a full load, that speed is called the full load speed or the rated speed. So in the nameplate details of induction motor, the given speed is called as the rated speed at the full load. The rated slip means slip at the full load. A rated slip is basically if you keep a full load, the slip at that full load is called the rated slip or the full load slip. So therefore, rated slip means the slip at the full load. So if you keep a full load, then whatever the slip, it is called as the rated slip or full load slip. Always in the induction motor, the speed that they are going to give you, it is the rated speed or the full load slip. Means if you full load speed. So if you correct a full load, then the speed at that full load is called as the full load speed or rated speed. In a slip ring induction motor, we inject the voltage from externally to the rotor. I have already told you, basically in the slip ring induction motor, we are going to inject the voltage. We are going to inject the voltage from the external to the rotor. It may be phase with the induced voltage, or it may be anti-phase or opposite phase with respect to the induced voltage. So listen carefully. We are going to basically externally inject the voltage in the rotor. If it is in phase, it can be phase with respect to induced voltage in the rotor, or it may be opposite in phase with respect to induced voltage. All these things I have already told you. So therefore, V2 dash is equal to V2 plus or minus E injected. V2 is called as the induced voltage in the rotor plus or minus E injected. Plus means both are in phase, minus means both are opposite in phase. So V2 is also called as the per phase induced voltage in the rotor, and V2 dash is called as the new per phase induced in the voltage, because of plus means both are in same phase, minus means both are opposite in phase. So this is the important point that you always have to remember. So V2 is always equal to E2. V2 we can get E2, or V2 dash is equal to E2 dash. You can go for the any of the notation, both are same. So now we will discuss another concept which is called the three-phase alternator. So in a three-phase alternator, for star connection, I have already told you the line voltage is equal to root 3 times the phase voltage. Phase voltage is under root over E1 square plus E5 square. So if you want the maximum value, just take the maximum values of each and everything. So in the star connection, see, I have already told you there will be no third harmonic. In the phase voltage, there will be basically in this line voltage is nothing but root 3 times the phase voltage. The phase voltage is under root over E1 square plus E5 square. There will be no third harmonic component in the line voltage. Whether it is a star connection or whether it is a delta connection, in the line voltage there will be no third harmonic component. So listen carefully. Whether it is a star connection or delta connection, in the line voltage there will never be third harmonic component. So therefore, EL is equal to root 3 into under root over E1 square plus E5 square. So if you want the maximum value, just take all these things as a maximum value. Then what is the RMS value? It is equal to maximum value by root 2. So therefore, you have to find the basically the maximum value, and you have to do a division by root 2. then you are going to get the RMS value. So therefore, I already told you whether it is a star connection or whether it is a delta connection. In the line voltage, there will be never third harmonic component. So therefore, EL is equal to root 3 into under root over E1 square plus E5 square. So take all the maximum values and then you are going to get the maximum value of line voltage. If you want RMS value, just take the maximum value by root 2. In the delta connection, I already told you the line voltage is equal to phase voltage. So the line voltage is equal to phase voltage. So therefore, under root over E1 square plus E3 square plus E5 square. So take all the maximum values. Take all the maximum values. And if you want the RMS value, just the maximum value by root 2, you are going to get the result. So this is a very important point. A small correction here, let me repeat here. I have already told you for star connection. See, for star connection, for 60-degree phase spread and the 100-degree phase spread, there will be no third harmonic component. That is what I am trying to tell you, not the delta connection. So therefore, in the star connection, for the 60-degree phase spread and the 120-degree phase spread, there will be no third harmonic component. So EL is equal to root 3 into under root over E1 square plus E5 square. Whereas in the delta connection, yes, there will be third harmonic component. So because if the delta means there is a closed path, so whenever there is a closed path, always the third harmonic component is going to get flow. So therefore, EL is equal to under root over E1 square plus E3 square plus E5 square. So take all the maximum values. If you want the maximum value, then the radiated voltage is equal to line voltage by the maximum value by root 2. So this is the point that I am trying to tell you from the starting onwards. So therefore, simply we can say that, so you have to consider even the third harmonic component also here. So you have to consider even the third harmonic component also, you have to always consider, which is equal to under root over E1 square plus E3 square plus E5 square. So now you have to consider even the third harmonic component also here. So therefore, here under root over E1 square plus E3 square plus E5 square. So always you have to take the maximum values and then divide by root 2, you are going to get the RMS values. So finally, I can say that in the 3-phase alternator in a star connection, so line voltage is equal to root 3 into under root over E1 square plus E5 square. So you have to take the maximum values to get the maximum value and divide by root 2, you are going to get the RMS value of the line voltage. In the delta connection, the line voltage is nothing but it is equal to under root over E1 square plus E3 square plus E5 square. If you want maximum value, take each and everything maximum value, and if you want RMS value, just divide by root 2 to get the RMS value. So what I am trying to say is basically here in a star connection for 60-degree and the 120-degree phase spread, in the line voltage there will be never third harmonic component. So this is the thing that I want to try to tell you. So for alternator, I have already told you for alternator, beta is called the slot angle, which is 180-degree by slots per pole, or simply 180-degree by pole pitch. Pole pitch means the number of slots per pole. So beta is called the slot angle, means it is the electrical angle between the two adjacent slots. And M is called as the, we can say it is called as the number of, basically it is called as the phase group, or we can say phase group means how many number of slots are associated per one phase under one pole. So listen carefully. M means it is called as a phase group. So therefore, phase group means the number of phases, the number of slots which are assigned for one phase under one pole, that is called as the M. So listen carefully. M means the phase group means the number of slots assigned for same phase under one pole. So M is equal to slots per pole per phases. It is going to tell you the number of slots which are assigned per one phase under one pole. The number of slots which are assigned per one phase under one pole, that is called as the M. The number of slots which are assigned for one phase for one pole, it is called as the M is called as the phase group. So therefore, here M is called as the slots per pole for phase means the number of slots under one pole as assigned for one phase. It is called as the M. So M into beta is called as the phase belt. So this is the angle. This is the electrical angle for which the one phase is going to get there in the one pole. So for this much amount of angle, for this much amount of electrical angle, the one phase is going to cover under the one pole. So T is called as the turns per. So turns means number of slots into conductors per slot by 2. So listen carefully. The turns is nothing but, see, number of slots into conductors is going to give you total number of conductors. But see, for one turn there is two conductors. So for one turn there are two conductors. For T turns you are going to get basically, so the number of slots into conductors per slot, it is going to give you total number of conductors. So therefore I have already told you here total number of conductors are this one, but I want turns, so divide by 2, you are going to get the total number of turns. So slots into conductors per slot, we are going to get total number of conductors by 2 we are going to do to get the value of turns, because in a one turn there are 2 conductors. So therefore we have to do by this one number of conductors by 2 to get the total number of turns. Suppose small example here. Suppose for one turn there are 2 conductors. So let me assume the total number of conductors are Z. The normal number of turns T. So do the ratio 1 by T is equal to 2 by Z, or simply T is equal to Z by 2. Total number of conductors by 2. So total number of conductors are slots into conductors per slot. This is called the total number of conductors Z by 2. You are going to get the total number of turns. So therefore simply for one turn there are 2 conductors. For T turns there are Z conductors. So therefore do the ratio we are going to get. So therefore T is equal to Z by. So total number of turns is equal to total number of conductors by 2. The total number of connectors is equal to slots into connectors per slot. We are going to get total number of connectors by 2 is nothing but the number of turns. But if you want turns per phase, total number of turns per number of phases are present. So turns per phase is nothing but total number of turns per the number of phases are present. So turns per phase is equal to total number of turns by number of phases. Kp is always equal to 1 for full pitch coil. I have already told you Kp is called as a pitch factor. The pitch factor general formula is equal to cos of n alpha by 2. So for full pitch, the short pitch angle alpha is equal to 0. So cos of 0 is equal to always 1 irrespective of the harmonic. So Kp is equal to always 1 for full pitch coil. So now we will discuss about the synchronous impedance of alternator. Synchronous impedance of alternator is Zs is equal to Rs plus Jxs. Synchronous impedance of alternator is nothing but Zs is equal to Rs plus Jxs. Synchronous impedance of alternator is nothing but Zs is equal to Rs plus Jxs. So if you want to know what is the magnitude of the Zs, the magnitude of Zs is nothing but it is the ratio of the open circuit voltage per phase by short circuit armature current at the rated IF rated current. So it is a constant value. The IF is a constant value. At this constant field current rated value, we are going to get open circuit phase voltage and we are going to get the armature current, or we can simply call it as a short circuit current or armature current. So if you do the ratio of these two things, we are going to get the value of Zs, which is basically the magnitude part. So therefore simply we can say that the Zs is equal to Rs plus Jxs. It is called as the synchronous impedance of alternator. The magnitude of Zs is equal to ratio of the open circuit per phase voltage by the short circuit current. It is also called as the rated armature current. At the IF is constant. IF should be always constant. At a particular IF constant value, we have to see what is the value of open circuit voltage and we have to see what is the armature current at the short circuit. Then if you do the ratio of these two things, this we are going to get from the open circuit characteristics and this current we are going to get from the short circuit characteristics. So if you do the ratio of these two things, we are going to get the value of the Zs, which is basically the magnitude part. So DC ammeter voltmeter test. So now we will see what is the DC ammeter voltmeter test. For a star connection, what is the phase resistance? Phase resistance is equal to Rm by 2. So R phase is called as the per phase resistance and Rm is called as the measured resistance between any two terminals. So whatever, see, suppose if these are the 3 terminals, star connection. So if I measure the resistance between any two terminals, each having a resistance of Rm and Rm. So Rm is equal to 2 into R phase. So R phase is equal to Rm by 2. It is called as the Rs. Rs is called as a synchronous resistance. So Rs we are going to get. Or simply we can also call as Ra or Rs. Anything is same. So Ra also you can call or Rs also you can call. Anything it is same. R is the resistance or stator resistance. Rs or Rm. Suppose for delta connection, then if you take any two things, each having a resistance of R phase and R phase. So R phase and R phase are series. So 2 R phase and this is again R phase. So if you do this one, we are going to get basically Rm is equal to 2 by 3 into R phase. So R phase is equal to 3 by 2 into Rm. It is equal to Rs. So like this you have to figure out. So for star connection, R phase is equal to Rm by 2. And here for delta connection, R phase is equal to 3 by 2 into Rm. It is equal to Rs. R phase is equal to Rs or Ra. You can use any symbol. So R phase is called as the per phase resistance. It is a per phase resistance. Rm is called as the measured resistance between any two terminals. So with the help of DC ammeter voltmeter test, we can figure out what is the per phase resistance, or we can say armature winding resistance or stator coil resistance. So each phase is going to have a resistance of Rs, or we can say Ra or Rs. So if you connect any two terminals with the help of DC ammeter voltmeter, you are going to get a resistance of Rm. Here Rm is nothing but 2 R phase. So R phase is called Rm by 2. R phase is nothing but Rs or Ra, anything which is same. Similarly for delta connection, if you connect a DC ammeter voltmeter test across any two terminals, This R phase and R phase are series. So 2 R phase and this other R phase. So both are in parallel. So therefore Rm is equal to 2 by 3 into R phase. So R phase is equal to 3 by 2 into Rm. R phase is nothing but Ra or Rs. So R phase is called as the per phase resistance and Rm is called as the measured resistance between any two terminals. Then what is the value of Xs? Xs is equal to under root over Zs magnitude whole square minus R phase whole square, because we know the value of Zs from the previous equation minus R phase whole square. R phase we can easily figure out with the help of DC ammeter voltmeter test. So if you solve here, we are going to get the value of Xs also. So this is the way that we have to find the value of Zs, Ra and also the Xs with the help of this test. So ISC is called as a short circuit armature current at the rated field current. So ISC is called as a basically short circuit armature current at the rated field current, and EOC is called as a open circuit. So EOC is called as the open circuit line voltage at rated field current, but you have to take only the phase value. So therefore we have to go for by root 3, EOC by root 3. So always remember we have to take only the phase value, but whatever the from the graph we are going to get the line voltage, so we have to divide by root 3 to get the phase value. So this is a very important value because we are going to only the per phase values. So whatever the things that you are going to get from the graph is a line voltage, but you have to go for divided by root 3 to get the phase value. So therefore EOC is called as the open circuit line voltage at the rated field current. See, field current is a constant for both these values. So field current is always constant for both these values and also it is rated. So with the help of this we are going to get the so by doing the ratio of these two things we are going to get the value of the mod of Zs, and from this we are going to get the value of Rs or Ra, and from this we are going to get the value of Xs or Xs. Basically it is called as a Xs. Rs is also called as the resistance of the stator coil, or basically we can also call it as the here armature resistance per phase. So synchronous impedance of alternator. So what is the synchronous impedance of alternator? See, here open circuit rated voltage we are going to get at IF1 current, and we can see this is called as the short circuit armature current at a rated field current. We are going to get at a current of IF2. Then what is the value of short circuit ratio? It is a ratio of the listen carefully. SCR is called as the short circuit ratio. Short circuit ratio is the ratio of the rated field current required to get the rated open circuit voltage by rated field current required to get the rated armature short circuit current. So listen carefully. Here SCR is nothing but it's a ratio of the rated field current required to get the rated open circuit voltage by rated field current required to get the rated armature short circuit current. So this is IF1 by IF2. So IF1 is called as the field current required to get the rated open circuit voltage, and IF2 is called as the field current required to get the rated armature short circuit current. So you can use it to basically field current. You can use basically field current, not the rated value. So basically what is the field current? So field current. So now you can just use the symbol field current. Don't have to use the rated because both are different. It may be same or it may be different. So therefore we can say that field current, SR is nothing but it is a ratio of the field current required to get the rated open circuit voltage by the field current required to get the rated armature short circuit current. So listen carefully. SCR is nothing but short circuit ratio. It is a ratio of the field current required to get the rated open circuit voltage by field current required to get the rated armature short circuit current. So SR is nothing but it's a ratio of the field current required to get the rated open circuit voltage by field current required to get the rated armature short circuit current. So SR is called as the short circuit ratio. So SR is called as the short circuit ratio. So SR is equal to, finally you are going to get which is 1 by Xs per unit. So finally you are going to get which is called as the 1 by Xs per unit. So finally you are going to get like this. SR is nothing but 1 by Xs in terms of per unit. This is in the unsaturation mode. Always in the unsaturation mode. I already told you what is the ISC rated. See, at IF2 you are going to get the ISC rated short circuit, or you can say the armature current, or you can say rated armature short circuit current is equal to S by root 3 into EOC rated. EOC rated you are going to get. So therefore simply here ISC rated is nothing but S by root 3 into EOC rated. S is equal to root 3 into VL into IL. So we have to use the rated of these two values. So these things that we can easily get from the IF1. So from the IF1 we are going to get this one. So therefore now what is the value of ISC? ISC is nothing but, so slopes are always equal, which is IS rated by IF2 is equal to ISC by IF1. Listen carefully. ISC rated by IF2 is equal to ISC by IF1. So this is the armature current which you are going to get at the IF1. So this is the armature current that we are going to get the IF1 because it's a straight line. I already told you, listen carefully, I already told you at IF2, as I already told you SSC, the short circuit graph is basically a straight line passing through origin for all the time. So now I already told you at IF2 you are going to get a rated armature current. So now at IF1 I already told you we are going to get a rated open circuit voltage. But now I want to find what is the current that you are going to get. What is the armature current that I am going to get at the field current IF1? Let me assume this is ISC. So it is straight line, so slope is equal. So ISC by IF1 is equal to ISCR by IF2. So ISC by, take IF1 here. So ISC by IF1 is equal to IS rated by IF2. Then we are going to get, after solving this one, so this is ISC is nothing but this is the ISC that we are going to get at the IF1. So same thing I have written. So now this is the equation that we are going to get. So this is the ISC at IF1 we are going to get. So from this characteristics itself. Then what is the value of mod of ZS? Mod of ZS I have already told you. Mod of ZS is nothing but it is the ratio of the open circuit phase voltage by short circuit armature current. You can take at any field current. So let me take at this field current. So I have already told you this is the IF1. At IF1 what is the open circuit voltage that we can easily figure out, and what is the armature current at this field current, which is ISC. So do the ratio of these two things we are going to get. See, at a constant field current we have to do. At a constant field current only we have to do the simplification. Then we are going to get the magnitude of the ZS. So listen carefully. The synchronous impedance of alternator is nothing but how to figure out. See from this data. See in the question they are given the rated open circuit voltage. It is basically line voltage they are going to give. So UOC is nothing but it is a rated value. So it is the open circuit rated voltage at the, this is basically line voltage they are going to give at field current IF1. So now the short circuit rated current at the IF2. So this is called as the armature, the rated armature short circuit current we are going to get, or simply IS rated at IF2. So now we have to see basically what is the short circuit ratio. Short circuit ratio is nothing but it is the ratio of the field current required to get the rated open circuit voltage by field current required to get the rated armature short circuit current. So simply it is nothing but from this data we can say it is ratio of IF1 by IF2. So for idea I can say that it is the ratio of the IF1 by IF2 because at the IF1 we are going to get the rated open circuit voltage, and at IF2 we are going to get the rated short circuit armature current, or simply armature, we can say rated armature short circuit current we are going to get. So SR is nothing but it's the ratio of IF1 by IF2, or we can also write another formula which is 1 by XS per unit value. So SR is also called as the short circuit ratio, or SR is also another formula which is 1 by XS into XS in terms of per unit. It is always unsaturated. So now here I have already drawn the graph with respect to this is called the short circuit characteristics. This is the graph. I am going to get a straight line passing through origin for all the time. So this is the field current and this is the armature current. So I have already told you at IF2 you are going to get a rated armature short circuit current. This is ISCR, which means ISC rated. Now at field current IF1 we are going to get a open circuit rated voltage. Now what is the corresponding armature current? Let me assume this is ISC. So now I have already told you here basically how to figure out the ISC rated is nothing but S by root 3 into VOC rated, because S is equal to root 3 into VL into IL. So IL is equal to S by root 3 into VL. So therefore if you take the rated voltage line voltage you are going to get the rated current. So therefore ISC rated is equal to S by root 3 into VOC rated. So from this you are going to get the ISC rated. But I have already told it's a straight line passing through origin, so slope is same, Y by X, which is ISC by IF1 is equal to ISCR by IF2. So what is the value of ISC? ISC is equal to ISC rated into IF1 by IF2. So this is the ISC corresponding to which one? At IF1, because at IF1 you are going to get ISC. So therefore this is the current ISC at corresponding to IF1. Then what is the value of ZS? I have already told you the magnitude of ZS is equal to, which is the ratio of the open circuit phase voltage by the ISC. ISC is nothing but it is the current which is corresponding to field current constant. This field current should be always constant. So at this IF1, what is the open circuit voltage, which is UOC per phase value means line voltage by root 3. Then what is the corresponding armature current, which is ISC. So This is the thing that you always have to remember. It is a constant field current. For a constant field current, we have to do the ratio of the corresponding open circuit voltage phase voltage by corresponding open circuit phase voltage by corresponding armature current, armature short circuit current, which is ISC in this case, corresponding armature short circuit current, which is ISC in this case. So like this that we have to always do in this format to get the value of this result. So now we will discuss an important concept. Listen carefully here. It's very much important. So here, let me assume this is a synchronous generator. The stator, basically the armature coil is going to place on the stator. It's a three-phase alternator. So this is connected in the star fashion. So this each having a resistance and also the reactance, which is RA and XS. RA is called as the armature reactance and XS is called as the synchronous reactance. It is per phase reactances. So this is the EL, which is the, we can say the line voltage which is induced, and this is the terminal voltage VL. So this is going to connect to a three-phase bus. So you can see clearly this is going to connect to a three-phase bus. The line current is IL and the terminal voltage is VL, and this is the induced voltage. The induced line voltage is EL. So we are going to send a complex power of S to this infinite bus bar. Then what is the complex power? S is equal to P plus JQ. It is equal to root 3 into VL into IL conjugate. So root 3 into VL into IL conjugate. So we are going to get S is equal to P plus JQ. These are the vector quantities, root 3 into VL into IL conjugate. So this here, so if you do the expansion of these things, if you keep the vector values and if you do the expansion, we are going to get a real part and also the imaginary part. This VL bar is a complex number. It is a vector value. I have already told you. So it's a vector value. So VL bar is equal to VL at an angle of 0 degree. I am going to assume like this. So now I will draw what is the per phase diagram. Per phase diagram I am going to draw, which is you have to take only RA, XS and this per phase and this per phase. So this line voltage is EL, but this is the phase voltage, which is EPH at an angle of delta I am going to assume. And this I have already assumed this is 0 degree. So this is the line voltage, but now phase voltage is equal to line voltage by root 3. Therefore VL by root 3 at an angle of 0 degree. And this is the line current IL. This is the armature resistance and synchronous reactance. So now let me assume this at an angle of delta. I have already told you in a synchronous machine, always E bar is always going to lead the VL. Now, always the induced voltage is always going to lead the terminal voltage. So this is D0, it is always going to lead. So angle is delta. So now I will write the EMF equation in this one. So based on the vector, or we can say EMF vector, KVL vector equation, we are going to get EPH at an angle of delta is equal to IL into RA plus JXS plus VL by root 3 at an angle of 0 degree. The delta is called as the load angle or the power angle. So delta is called as the load angle or power angle. So EPH is nothing but EPH means it is EL by root 3. EPH means EL by root 3. So delta is called as load angle or the power angle, or simply it is also called as a torque angle. It is a phase angle between the EPH and VL. So therefore simply we can say delta is the phase angle between the EL and VL, or EPH and VPH. Terminal voltage, see the phase voltage of terminal and the induced voltage phase value, whether there can be line voltage or whether there can be phase voltages. And now the angle is again same, which is delta. So delta is the phase angle between the EL and VL. So it is also called load angle or the power angle. So now you can see clearly. So if you do the analysis, if you keep the S is equal to P plus JQ is equal to root 3 VL IL conjugate, finally you are going to get an expression P is equal to mod of EL mod of VL by mod of ZS cos of theta minus delta minus mod of VL whole square by mod of ZS into cos theta. So like this that you are going to get, basically this is the equation that you are going to get. And Q is equal to mod EL mod VL by mod ZS sin of theta minus delta minus mod of VL whole square by mod of ZS sin theta. ZS is nothing but RA plus JXS. So mod of ZS is nothing but simply ZS is equal to RA plus JXS. It is equal to mod of ZS at an angle of theta. Actually here let me write this is theta S. This is basically theta S. It is very much sufficient. So therefore which is called the synchronous impedance of the alternator. So basically all this theta I have replaced by theta S, because always it's a convention. This is mod of ZS and this is angle of theta S. So this is called a synchronous impedance of the alternator. So this is called as a synchronous impedance of the alternator. It is in the rectangular format and this is in the polar format. So this is the active power which is centered by the R3 phase alternator to the infinite bus bars. So this is the active power which has been sent by the three-phase alternator to the infrared bus, which is this is the active power and this is the reactive power, and this is the synchronous impedance RA plus JXS. So all these things I have already told you. This is theta S, theta S, theta S and theta S. Now what happens suppose if RA is equal to 0? If I substitute RA is equal to 0 here, so now the special case is suppose if RA is equal to 0, then definitely mod of ZS is equal to XS and theta S is equal to 90 degree. So if I substitute all these things here, cos 90 is nothing but cos 90 is equal to 0. So this is going to get happen. So cos of 90 minus delta is nothing but sin delta. So we are going to get P is equal to mod of EL by XS into sin delta. So this is the active power which is being sent whenever the RA is equal to 0, and Q is equal to mod of VL by XS mod of EL cos delta minus mod of VL. So Q is nothing but the reactive power, which is this is the active power is equal to mod of VL by XS sin delta, and the reactive power is equal to simply here mod of VL into mod of EL by XS into cos delta minus mod of VL square by XS. So Q is equal to mod of VL into mod of EL by XS into cos delta minus mod of VL square by XS. So this is the equation that you are going to get here if you simplification. So therefore Q is equal to mod of VL into mod of EL by mod of XS into cos delta minus mod of VL square by XS. So this is the equation that you are going to get. So if RA is equal to 0, whatever the input power is equal to output power, and also here the reactive power, this is the output reactive power. If you want the input reactive power, which is very simple, mod of EL square by mod of XS minus mod of VL into mod of EL by mod of XS into cos delta. So these things I have already told you, very simple. This is the output active power, this is the output reactive power. Whenever RA is equal to 0, input active power is equal to output active power, and the input reactive power is equal to mod of EL whole square by mod of XS minus mod of EL into mod of EL by mod of XS into cos delta. These things I have already told you in the previous class only. So therefore, this is the active power which has been sent to the infinite bus bar, and this is the amount of reactive power which is sent to the infinite bus bar. So now we will discuss a small important concept. So listen carefully here. It's a very small important concept that is always very much useful. Here EMF is varied, means excitation is varied. As I have already told you, if you vary the excitation, what is going to change is IA is going to get changed, and the IF is going to get changed, and the power factor is going to change, and the nature of the power factor is also going to get changed. So this is basically here. See, excitation is always constant. The excitation is always constant. Means, see, the EMF excitation is varying, but the mechanical input is always constant. So mechanical input is always constant. It is a three-phase alternator. As we are going to give the mechanical input in the terms of rotation, it is a constant one. So this on the stator we are going to keep armature coil. So we are going to connect to a load. So this is the terminal line voltage, and this is the line current IA. Then let me assume the load one. The load one is basically UPF. Let me assume whatever the load one, initial load is nothing but UPF load. Then I have already told you here the constant we are going to basically see, we are going to give a constant mechanical input. So active power is always constant. So active power is always constant whether you increase the excitation or not. Even if you change the excitation, always this value is always constant. Then if I apply the per phase EMF equation, EPH bar is equal to, which is this is the line voltage. So I will go to the phase, which is VT by root 3 at an angle of 0 degree. I am going to assume plus, as it is the UPF load, so I at an angle of 0 degree, which is RA plus JXS. It is nothing but equal to, I have already told you, in a synchronous generator, EPH is always going to lead the terminal voltage. It is assumed that EPH1 at an angle of delta 1 I am going to get here. Then what is the amount of single phase power? The single phase power, if you want to know what is the single phase power which has been transferred from the input to this output. So how much amount of active power which is received by this single phase power received by the load is nothing but, here you have to use the phase values. If you want the single phase, you have to use the phase values, but if you want the three phase, you have to use the line values. Very simple concept. Listen carefully. Here when you want the single phase power, then you have to use the phase values. If you want three phase power, then you have to use the line voltage values, which is EPH1 into VT per phase, which is VT by root 3 by XS into sine of delta 1. Delta 1 is the phase angle between the EPH and the VT by root 3. So we can simply say EPH and VTPH phase voltages. Then you are going to get some constant value. Some constant value we are going to get here. I already told you here, whenever the mechanical input is a constant, see, I already told you one important point. This E value is going to get vary, and excess is going to get vary. And this is the constant. The input, the power is always constant, irrespective of the variation of the EMF. So definitely, what should be constant? Then this V is a constant. See, this V is a constant. The terminal goes slow. This terminal voltage will be always constant. Then EPH1 into sine delta 1 is always equal to EPH2 into sine delta 2. These things I have already told you. See, VT is the terminal voltage is a constant, X is a constant, and the P is a constant. Then this voltage is also has to be constant, which is EPH1 into sine delta 1 is equal to EPH2 into sine delta 2. This EPH1 into sine delta 1 is equal to EPH2 into sine delta 2. Suppose I go for the load 2. Suppose if I go for the load 2, if I keep another load, then what is the new armature current? We have to use the phase values. Let me ask same thing. The terminal voltage is always same, which is VT by root 3 at an angle of 0 degree. Here minus EPH2 at an angle of delta 2. So whenever you change the load, definitely let me assume the terminal voltage is a constant. So you are going to change the per phase because we are going to change the excitation also. So EPH2 at an angle of delta 2 is RA plus JXS. So if you solve this one, we are going to get IA2 at an angle of some theta 1. The theta 1 is the power factor angle between the terminal phase voltage and the armature current. So what is the power factor? The power factor of the load is nothing but cos of theta 1 for load 2. So what is the power factor? Power factor is the cos of theta 1. It is a phase angle between the terminal phase voltage and the terminal current. So from this we can get the power factor of the load is equal to cos of theta 1. So this is for the load 2. So with the help of this one, we can figure out the power factor of the load 2. So this is cos theta 1. So this is the concept that you always have to understand to solve this type of questions. So what I am trying to say basically very simple. Whenever the mechanical input is a constant, then the active power is a constant and the terminal voltage is also constant, X is a constant. So this product is also constant. EPH1 into sine delta 1 is equal to EPH2 into sine delta 2. Well, I think in the question they are given the EPH1, delta 1 and delta 2. So we have to find EPH2, and from this we have to keep it here in this equation, and if you solve this one we are going to get the new armature current and also power factor angle. It is a theta 1 is a phase angle between the terminal phase voltage and the armature current. So from this we are going to get the power factor of the load, which is cos of theta 1 is for the load 2. So this is the concept that you always need to understand in order to solve this type of numericals. So now we'll discuss some important concept here. Just small concept here. I've already told you this is basically a 3-phase alternator. So whatever the stator coil, or you can say the armature coil present on the stator is a star connected. So we are going to connect a load. The load has a power factor of cos phi, or we can say cos theta or cos phi. Theta is the phase angle between the terminal voltage and the terminal current, which is Vt and Ia. So basically, generally we are going to use the theta here, not cos phi. The theta we are going to use here. So power factor of the load is equal to cos theta, but theta is the phase angle between the terminal phase voltage and the we can say the load current Ia. So now if I draw the per phase diagram, for a per phase, this is armature resistance Ra, the synchronous reactance XS, and this armature current Ia, and this is the EMF induced per phase value, and this is the terminal per phase voltage. So now I am going to write the EMF equation in this loop. Then EPH bar is equal to VPH bar plus Ia bar into Ra plus JXS. Then if I basically now what I am going to do, basically I have already told you the EMF equation. The EMF equation I have already told you, I think you have remember, which is EPH square is equal to EPH is equal to under root over VPH cos phi plus Ia Ra whole square plus VPH sin phi plus or minus Ia XS whole square. This thing I have already told you. The EMF induced the EMF equation, which is basically, listen carefully, I have already told you, which is here F is equal to under root over V cos theta plus Ia Ra whole square plus sin theta plus or minus Ia into XS whole square. These things I have already told you. Here where EF is nothing but the induced EMF per phase value. Those are all the per phase values, and we have already told these are called as a per phase terminal voltage. And here basically this is cos theta, not cos phi. Here actually it is a theta. You have to use the symbol theta. So theta you should always use. Theta is the phase angle between the terminal voltage and the terminal current. So therefore we can say simply it is a power factor of the load. So I have already told you EF is equal to under root over V cos theta plus Ia Ra whole square plus V sin theta plus or minus Ia into XS whole square. These things I have already told you. Where EF is nothing but EMF induced per phase value, and V is nothing but the terminal voltage per phase value, and theta is the power factor of the load. And I already told you that Ia bar is nothing but the current value. Ia bar, you have to take the magnitude only value that you have to consider. So this is the equation that you are going to get. Then what I have to do basically here, this place is for the lagging load. I already told you, minus is for the leading load. This is for the generator. This is for the generator. Suppose if If is equal to constant, then I have already told you Eb is always constant, because whenever the excitation is a constant, then whatever the EMF that you are going to induce, the per phase value is also constant, or we can say terminal voltage is also constant. So based on this, we are going to find see, if you know each and everything, then you can get the per phase terminal voltage, you can easily figure out. Then if you want the line voltage, which is √3 into phase voltage, see basically we have to find always the line voltage, the amount of the terminal voltage is that it is nothing but line voltage is equal to √3 into phase voltage, the phase voltage of the terminal voltage. So from this equation, we are going to find what is the value of the terminal phase voltage, and if you keep here, if you multiply by √3, you are going to get the terminal line voltage. So this is the concept that you always have to remember. Whenever the If is a constant, flux is a constant, then EMF induced per phase is also constant. So these things I have already told you. So like this, you have to solve this type of numericals. So let me tell you a small important concept here. Small important concept. Always the complex, see the complex power generated, the summation of all complex power generated is equal to the summation of all complex power demand. Whenever the losses are neglected, so we are going to neglect the losses. So always the summation of all complex power generated is equal to summation of all complex power demanded. So we can say that here these are all basically vector quantities. All these are the vector quantities. So we can say that if you go for all the real parts and imaginary parts, so finally we are going to get the summation of all power active power generation is equal to summation of all active power demand. Similarly, the summation of all reactive power generation is equal to summation of all reactive power demand. So the summation of all active power generation is equal to summation of all active power demand, and summation of all reactive power generation is equal to summation of all reactive power demand. So I have already told you, we have to use the symbol positive for the lagging nature, and minus you have to use for the leading nature. These things I have already told you in a very detailed manner. See, I have already told you, suppose if you take a voltage as a reference phasor, for lagging load, current is going to get lag. So therefore, let me assume V is equal to B at an angle of 0 degree. So V bar is equal to B at an angle of 0 degree, and I bar is equal to I at an angle of minus theta. So if you take the complex conjugate, I have already told you complex conjugate means simply here we have to take B into IL, I at an angle of minus theta whole conjugate. Then we are going to get B into VL into IL into B into I into at an angle of plus theta. So therefore, plus is used for the lagging nature, minus is used for the leading nature. These things I have already told you. So therefore, whenever positive, always the angle positive we have to use for the lagging nature, and minus we have to use for the leading nature, because let me assume the voltage is equal to V bar is equal to B at an angle of 0 degree. Let me assume it's the lagging node. So current is going to get lag. So I bar is equal to I at an angle of minus theta. So therefore now the complex power is equal to VI conjugate. So therefore simply VI conjugate is nothing but just you have to go for this conjugate of current. I at an angle of minus theta whole conjugate is nothing but VI at an angle of plus theta. So now plus is used for the lagging nature. So minus is used for the leading nature. So this is the way that you always have to understand. So now let me draw what is the power flow in the alternator. So let me draw what is the power flow in the alternator. See, I have already told you in the alternator. Alternator means the shaft is going to rotate. The shaft is going to rotate. So we are going to rotate the shaft. The input power is the shaft power. So now there will be some rotational losses. So some power is going to go in the terms of rotational losses, and the remaining power, it is called as the developed power. The remaining power is called as developed power. Again, the power developed is nothing but EF into, or we can say EF into IA. This is the power developed. But again, there will be some copper losses, and then whatever this is called as the output power. So this is the diagram of the active power flow in an alternator. So this is the shaft power, input shaft power, and this is the rotational losses, and this is the actual electrical power developed. This is the mechanical input, and this is the electrical power developed. There will be some certain copper losses in the windings, and then we are going to get output. What is the output power? Now power flow in the alternator. See, I have already told you power flow in the alternator is nothing but this is the shunt power. It is a shaft power. Basically, it's a shaft power. So out of the shaft power, it is the mechanical power. So then there will be small amount of rotational losses. Here it is the electrical power developed. Again, there will be some copper loss in the winding. Again, you are going to get finally the output power. So now whatever the here PF plus QF. So PF is nothing but which is the field winding. In the field winding, you are going to give some active power and also the reactive power. See, whatever the active power is lost, whatever the field active power is lost in the terms of heat, it is going to get lost. Whereas the reactive power, it is going to utilize for making the flux. So therefore, in the field winding, we are going to give the active power and also the reactive power. But the active power, it is going to last in the term of heat in the field winding. But the reactive power, we are going to generate the flux and we are going to utilize it. So therefore, QF is utilized, but PF is lost. The active power in the field winding is lost, whereas the reactive power in the field winding is utilized for making the flux in the air gap. So therefore, this is called as the PROT is called as rotational losses and PCU is called as the copper losses in the winding. The rotational power is equal to the summation of core loss plus friction and windage losses. So listen carefully. I already told you a very important point. Rotational loss means it is the summation of the iron loss and also the friction and windage loss, or simply we can say mechanical loss. So the rotational loss means it is the summation of the iron loss plus mechanical loss. So mechanical loss is also called as the friction and windage losses. So therefore, the rotational power is equal to the core loss power plus mechanical power is also called the friction and windage losses. Then what is the power in the active winding? So we can say in the field winding, the power loss in the field winding is equal to field voltage whole square by the resistance of the field winding. So therefore, the power loss in the field winding is equal to the field winding voltage whole square by the resistance of the field winding. Then what is the efficiency? Efficiency of this alternator is equal to output power by input power. See, output power is P out. The input power is nothing but here. The input power is nothing but output power plus losses, which is output power plus losses. How many losses are there? Basically, copper loss is there, and the rotational loss is also there, and one more loss which is called as the PF. PF is called as the power loss in the field winding. So we have to consider all these losses. So listen carefully. The efficiency is equal to efficiency of the alternator is equal to output power by input power. Output power by input power is equal to output power plus losses, which is output power plus losses are nothing but copper loss is there and the rotational loss is there. And one more thing is here nothing but this overall summation is called as this P output plus P rotational plus PCU is nothing but very simply we call this as the shaft power. This is the shaft power that we are going to give, and also we are going to give we can say we are also giving the active power to the field winding also we are going to give. So we have to add these two things, the shaft power and also the active power given to the field winding. So you have to add even these two inputs. So they are going to get the overall input. This is called as the overall input, active power input to the alternator, which is here efficiency is equal to output active power by input active power, which is total active power input to the alternator is nothing but the shaft power plus also the active power loss in the winding, which is the shaft output power is not the shaft power is nothing but output power plus rotational losses plus copper loss. This is called as the shaft, or you can say the shaft power plus the power loss in the field winding. It is also PF. So we have to add this both the power inputs. So this is called as the output power by total input power. This is called as the shaft power and this is the power loss in the field winding. So you have to add these two things. This is the overall input, active input to the alternator. So this is the efficiency of the generator. So now we are going to see about the power flow in the synchronous motor. So now we are going to see what is the power flow in the synchronous motor. In the synchronous motor, initially we are going to give the electrical power. So there will be some copper losses and this is the electrical power developed, or we can say the mechanical power developed. Again there will be some rotational losses. Again we are going to get shaft power. So you can see this diagram is simpler. It is the reverse of the alternator. So we are going to give electrical power. Here you are going to get copper losses. Here you are going to mechanical power developed, and here it will be rotational losses. Here you are going to get the shaft power. It is basically the same principle, but it is a reverse one. It is a reverse of the previous graph. And here we are going to give the active power to the field winding and also reactive power to the field winding. I have already told you the active power to the field winding is lost in terms of heat, whereas the reactive power input to the field winding is utilized for making the flux. So this diagram is reverse of the previous diagram, but this is same as the previous one. So this is the point that you always have to understand. So this diagram is the reverse of the previous one, but this is same as the previous one. So electrical power that you are going to give, there will be some copper losses, then you are going to get some mechanical power developed. Here there will be some rotational losses, and here you are going to get the shaft power. Here you are going to get the shaft power. So now what is the shaft power? Shaft power is nothing but the mechanical power developed minus rotational losses. You can see clearly the shaft power is nothing but the mechanical power developed minus rotational losses. Then if you want the shaft power to be maximum, See, I've already told you the rotational losses are same constant values from no load to full load. It is always constant. So if you want shaft power maximum, then definitely whatever the power developed will be maximum. Then only you are going to get a shaft power of maximum, because the rotational loss is always constant from no load to full load. So we can say if you want a shaft power of maximum value, then the developed power should be always a maximum value. And I already told you this is the diagram for a generator. This is the basically a diagram for a generator. This is the diagram for a generator. This is the diagram for a synchronous generator. This is the phase voltage, EMF induced per phase voltage, and this is the terminal voltage, and is the RA and JXS. This is for a generator, synchronous generator. So now what is ZS is equal to RA plus JXS is equal to mod of ZS at an angle of theta s. Then what is the power developed? Power developed. See, power developed is nothing but, actually this has to be reversed. This is actually V and this is actually E. See, I have already told you this is basically a synchronous motor diagram. This is the synchronous motor diagram. This is the supply voltage and this is the EMF induced. These are the per phase values. So now I have already told you here B is always going to lead the E in case of synchronous motor, whereas in generator E is going to lead the V. But here V is always going to lead the E in the case of synchronous motor. Then what is the electrical power developed? We can say mechanical power developed is nothing but, which is this vector into this vector. I have already told you the complex power. Complex power is nothing but here EL and E root 3 into EL into IL conjugate. I have already told you root 3 into EL into IA conjugate. But if you do that one, and finally you are going to get an equation which is called as the power developed is equal to 3 into E phase into V phase by mod of ZS cos of delta minus theta s minus 3 of EPH whole square by mod of ZS cos of theta s. So this is the equation that you are going to get if you want to know what is the electrical power, or you can say the mechanical power developed, which is, this is the equation that you are going to get. See, I have already told you all these crazy things. These things I have already told you. I hope you have remembered this formula. Basically same thing I have already told you, the basic equation. Listen carefully. I have already told you the amount of electrical power developed is nothing but S is equal to the complex power developed is equal to S is equal to root 3 into EL into IA conjugate. So if you do this one, finally, I have already told you the amount of active power injected is nothing but here I have already told you, which is mod of VL into mod of EL by mod of ZS cos of delta minus theta s minus mod of EL whole square by mod of ZS cos theta s. So this is the equation that you are going to get. So this derivation I have already told you, which is mod of EL into mod of EL by mod of ZS. This is mod of ZS into cos of delta minus theta s minus mod of EL whole square by mod of ZS into cos theta s. So mod of EL into mod of EL by mod of ZS into cos of delta minus theta s minus mod of EL whole square by mod of ZS into cos theta s. See, VL is nothing but root 3 into V phase. EL is equal to root 3 into E phase. So VL is equal to root 3 into V phase and EL is equal to root 3 into V phase, E phase. So finally I am going to substitute VL is equal to root 3 into V phase and EL is equal to root 3 into E phase. Then this equation is going to become this equation. So in this equation, if you substitute VL is equal to root 3 into V phase and EL is equal to root 3 into E phase, then finally you are going to get in this equation, which is 3 into E phase into V phase by mod of ZS cos delta minus theta s minus 3 E phase whole square by mod of ZS cos of theta s. This is the equation that you are going to get from this one. So this is what I am trying to tell you. So this is the equation that you are going to get from this one. So this is a very important equation. This is the power which is developed. So this is the power which is developed, the mechanical power which is developed. This is called as the mechanical power which is actually developed. Then I already told you maximum developed power. Then what is the maximum developed power? Whenever the delta is equal to theta s, you are going to get the maximum power developed. Then if you substitute here delta is equal to theta s, it is going to become cos 0 is equal to 1. Then if you substitute in the remaining equation, we are going to get the maximum power developed is equal to 3 into E phase into V phase by mod of ZS minus 3 into E phase whole square by mod of ZS into cos theta s. So this is the equation that you are going to get from this one. So this is a very important one. This is a general equation. From this we have got this one. So this is the way that you always have to understand the concept behind this one. So now we are going to discuss about the single phase alternator. So single phase alternator, we are going to see the diagram. I have already told you this is the EMF induced and is the RA and JXS and is the IA bar and is the terminal voltage. It is the phase voltage. These are the per phase, or we can say single phase alternator. So this is EMF induced and this is the terminal voltage. I have already told you here always in an alternator E is always going to lead the B. E is always going to lead the B. So therefore here the ISC at IF. So we are going to get, I have already told you the ISC at IF because at the field current at the short circuit test. So at particular IF we are going to get the armature short circuit. The rated armature current is ISC and the same IF we are going to get EOC. I have already told you then what is ZS? ZS is equal to RA plus JXS. Then mod of ZS is equal to EOC by ISC. So these are per phase values. So per phase value means simply we can say the line voltage is equal to phase voltage, but actually you have to take your phase. But it is single phase alternator. So whatever this value is same as this value. But whenever it's a, if it is not a three phase alternator, always then you have to use the per phase values only. The per phase EOC value you have to take. But here it is a single phase alternator. So per phase voltage is equal to EOC itself. So EOC by ISC. So EOC is called as the at a constant IF. At a constant IF, at a particular IF, what is the open circuit voltage and what is the corresponding, what is the short circuit current, armature short circuit current. So if you do the ratio of these two things, we are going to get the amount of ZF. So listen carefully. At a particular IF, you have to do the ratio of the open circuit voltage, which you are going to get from the OCC curve, and this is called as the armature, the short circuit armature current at that particular IF. So if you do the ratio of these two things, we are going to get the magnitude of the ZS. Then what is XS? XS is equal to under root over mod of ZS whole square minus RA square. In the question, they will be given RA. So from this, we get the value of the XS. So from this, you can easily get the value of the XS. Then if you write the EMF equation, I have already told you, which is E at an angle of delta is equal to B at an angle of 0 degree plus IA bar into RA plus JXS. So from this equation, we are going to get the value of E also. Then what is the voltage regulation? E minus V by V into 100. These things I have already told you. This E minus V by V into 100. This is the EMF induced and this is the terminal voltage. E minus V by V into 100 is called as the percentage of voltage regulation. So now we are going to see about the governor characteristics of the alternator. I have already told you whenever the load demand increases, the frequency will decrease. So at no load power demand, so whenever there is no demand, then the frequency is nothing but FNL, no load frequency, and the point is nothing but this is x-axis and this is y-axis, so 0 comma FNL, no load frequency. Suppose at full load, suppose if you apply a full load, then the frequency is going to get decreased, then the corresponding point is nothing but power at full load and the frequency of the full load. So if you want any general point, then x-axis and y-axis, which is P comma F. At this point the power is P and the frequency is F. Then see, now I want to find what is the basic equation. See, I have already told you this is a straight line, so slope is always equal. So this is called as the FNL minus FFL by PFL. So this axis is nothing but from here to this point. This length is FNL minus FFL by this length is nothing but PFL. Again, if you want to define this value, which is this length, which is FNL minus FF, and this is the by P. So you have to basically equate in the slope of this triangle and find the slope of this triangle and the slope of this triangle, both are equal. So therefore I am going to get these two equations, and if you solve this one, we are going to get the P is equal to FNL minus F by FNL minus FFL into PFL. So by this we are going to get at this particular frequency what is the power which is being the demand we can easily figure out. And what is the percentage droop? Percentage droop is nothing but from no load to full load, how much amount of change with respect to FNL. So FNL minus FFL by FNL into 100. The percentage of droop is nothing but how much amount of change from no load frequency to full load frequency with respect to no load frequency, which is FNL minus FFL by FNL into 100. It is called the percentage of the droop. So now we will discuss about the synchronous motor. This is the per phase diagram. So here this is called as the supply voltage, terminal voltage, and this is the EMF induced. So therefore this is called as a VPH and this is the EPH. These are all vector conjugates and this is RA, JXS and this is the IA bar. I have already told you in a synchronous motor always V is always going to lead the E. V is always going to lead the E. So if you write the EMF equation, EPH is nothing but VPH bar minus IA bar into RA plus JXS. Then what is the maximum power? Maximum power I have already told you. See, in a three phase, I am asking about the three phase maximum power. Three phase maximum power is nothing but, so three phase maximum power is nothing but here line voltage, both the values product line voltage by here XS into, so this is called as the mod of EL bar into mod of VL bar by XS is called as the maximum three phase power. This is the maximum three phase power, but EL bar is nothing but root 3 into E phase and VL bar is equal to root 3 into V phase. So root 3 into V3 is nothing but 3. So 3 into mod of EPH bar into mod of VHP bar by XS. This is called as a single phase maximum power. EPH bar magnitude into VPH bar by XS is nothing but it's a single phase maximum power. If you want three phase maximum power, just multiply by 3. So this is the overall three phase maximum power. This is basically the overall three phase maximum power. Whenever this is the equation only when RA is equal to 0. So this is the equation that you are going to get whenever the RA is equal to 0. So finally we can say the maximum power which is absorbed by this, the maximum active power. See, whenever RA is equal to 0, whatever the input power is equal to output power, the maximum power which can be sent is nothing but the three phase maximum power is equal to mod of EL bar into mod of VL bar by XS. So if you want in terms of phase, just EL is equal to 3 V phase, VL is equal to 3 V phase. So we are going to get 3 into EPH bar into mod of VH bar by XS. So this is called as the maximum three phase power. But this individual term, this EPH bar mod of VPH bar by XS is called as it's a single phase maximum power. If you do multiplication by 3, you are going to get three phase maximum power. So this is called as the three phase maximum power.
Now we'll discuss about the silent pole synchronous machine for generator. The tan psi, this is called as basically I am going to call it as a tan psi. So tan psi is equal to V. Here basically phi is nothing but theta. So phi is nothing but theta. So you can assume either phi or either theta, both are same. So I am going to assume that phi is equal to theta, which is the power factor angle between the terminal voltage and the armature current. So this is called as the phi is always equal to theta, which is called as the phase angle between the Vt and the Ia. So V into sin theta or sin phi plus or minus Ia into x cube by V cos phi plus Ia Ra. So we have to use the symbol plus for the lagging load and minus for the leading load. Always this psi is nothing but delta plus phi. So always I always told you delta is nothing but it's a load angle. It is a phase angle between the EF and the V. And phi is always equal to theta, which is called as a power factor angle, which is the angle between the V and Ia. And psi is nothing but it is a phase angle between the EF and the Ia. So this delta is called as load angle or torque angle, and theta is a power factor angle. And the psi is nothing but it is the internal power factor angle, because it is the angle between the EF and Ia. So it is called as the internal power factor angle, and this is the power factor angle, and this is called as the load angle or torque angle. Suppose when always psi is equal to delta plus phi. So this is the convention that we are going to use. Psi is equal to delta plus phi. So when Ra is equal to 0, we are going to get EF is equal to V cos delta plus ID into XD. So EF is equal to V cos delta plus ID into XD. Then ID is equal to IA into sine of delta plus phi. Delta plus phi is nothing but psi. So therefore IA into sine psi. So psi is called, the delta is called as the load angle. See, this symbol I am going to call it as the psi. So this is basically psi, I am going to call it as a psi. So therefore delta is called as the load angle or torque angle. So this is the equation for generator. So whenever the Ra is equal to 0, so we are going to get like this, which is EF is equal to V cos delta plus ID into XD. ID is equal to IA into sine of delta plus phi is equal to IA into sine psi, and delta is called as the load angle. See, for motor, the tan psi is nothing but V sin phi minus plus IA into x cube by V cos psi minus IA into Ra. See, you can use plus or minus or plus, anything is same. Just now the minus is for the lagging load and for the plus is for the leading load. Just interchange here, just we are going to change this plus to minus, that's it. This is same as the previous, just keep plus or minus here. Nothing is going to get happen. So in the previous equation, just here replace plus by minus, and here in the previous case it is plus is there. So just replace plus by minus and minus by plus. So now minus is for the lagging load and the plus is for the leading load. So in the previous equation, just here replace this plus by minus, and here it is a plus is there, now it's become minus, it minus is there, so it is become plus. So this is the only thing that you always have to understand, and this is same, psi is equal to delta plus phi, and V is called as the terminal phase voltage. All these are the phase voltages, So this is the equation for the generator. Tan psi is equal to V sin phi plus or minus Ia into x cube by V cos phi plus IRA. So in this equation, just we have replaced plus by minus and minus by plus, and remaining everything is same. So we have replaced here plus by minus and minus by plus, and remaining everything is same. So therefore, if you replace this plus by minus and the plus by minus and minus by plus, we are going to get for the motor. So this is something that you always have to remember. So now we will give some summary regarding these important things. So now let me give you conclusion regarding the generator and the motor. So generator in the lagging mode and generator in the leading mode. This psi, delta and phi. Psi, delta and phi. So this is plus, plus, plus. This is plus, plus and minus. So now here for motor lagging and leading, this is plus, minus, plus, and this is plus, minus, minus. So this is a symbol that you always have to remember. It is a sign convention. So therefore, here for generator lagging and leading, so this is plus, 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 minus, minus, plus, minus, plus, minus. So easy way to remember, plus, 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 minus, minus, plus, minus, plus, minus. So for generator leading, and for motor lagging, leading. So this is the way that you always have to remember. This is psi, this is delta, this is phi. Phi is nothing but equal to theta. That I have already told you. It is a theta. So therefore, simply we can say this is a generator, this is a motor, lagging load, leading load, lagging load and leading load. So this is plus, 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 minus, minus, plus, minus, plus, minus. So therefore, like this, that you have to always do this one. Let me assume plus is equal to 0 and minus is equal to 1. So plus is equal to 0, minus is equal to 1. We are going to get plus, 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 minus, minus, plus, minus, plus, minus. So you have to remember this table. Then everything is, see, this is basically sign sensitive. So like this, you have to substitute in the psi is equal to delta plus phi. These things I have already told you. Psi is equal to delta plus phi. So psi is equal to delta plus phi. Psi is equal to delta plus phi. So you have to replace with the sign sensitive. In whichever the thing that you have to replace the psi with the positive or negative like this, you have to substitute in that equation. So now we are going to see the slip test on the silent pole motor. I have already told you the slip test is basically we are going to turn on the silent pole alternator to figure out the direct axis reactance and the coordinate axis reactance. I have already told you in the English alphabets D is going to come earlier than Q. So always X2 is always greater than XQ. If this is greater means the ratio will be maximum by minimum. Here Q is minimum means minimum by maximum. So this is V maximum by I minimum, V minimum by I maximum. So XD is called as a direct axis reactance and XQ is called as a coordinate axis reactance. All this V max, V minimum, I max and I minimum are always these are all the phase values. Always these are the phase values. So now we will discuss one more important concept here. Whenever the silent pole alternator is connected to an infinite bus. So whenever the silent pole alternator is connected to an infinite bus, then what is going to happen? Now we will see what is the basic thing. The silent pole alternator connected to an infinite bus. I have already told you it is an alternator. So this is basically it's alternator. So this is the per phase diagram RA, JXS, and this is the armature current IA, and this is the terminal voltage, and this is the EMF induced. This is the per phase diagram we are going to draw. I have already told you in the alternator always E is always going to lead the V. So now suppose let me assume when RA is equal to 0, what is going to happen? See, whenever RA is equal to 0, the power equation, the amount of power delivered to the load in case of silent pole alternator is nothing but P is equal to E into V by XD. The XD net reactance into sin delta minus V square by 2 into 1 by XQ net value minus 1 by XD net value into sin 2 delta. These things I have already told you. So therefore, P is equal to EV by XD net into sin delta minus V square by 2 into 1 by XQ net minus 1 by XD net into sin 2 delta, where XD net is equal to XD plus XS and XQ net is equal to X2 plus XS. So this is the point that you always have to remember. XD net is equal to XD plus XS and X2 net is equal to X2 plus XS. So this is something that you always have to remember. Then the amount of power which is delivered to the load. So whenever RA is equal to 0, whatever the power generation is equal to power output also. So P is equal to E into V by XD net into sin delta minus V square by 2 into 1 by X2 net minus 1 by XD net into sin 2 delta. So XD net is equal to XD plus XS and XQ net is equal to XQ plus XS. The delta is called as the load angle or the power angle or torque angle. So delta is called as load angle or power angle or torque angle. So this is the easy formula that you always have to remember for the silent pole alternator whenever the RA is equal to 0. So whenever RA is equal to 0, whatever the input power is equal to output power. So this is the basic equation that you are going to get. This is basically we are going to call it as a three-phase power. So P is equal to E into V by XD net into sin delta minus V square by 2 into 1 by XQ net minus 1 by XD net into sin 2 delta. XD net is equal to XD plus XS and XQ net is equal to XQ plus XS. Delta is called as load angle or the power angle. See, in a three-phase, three winding transformer, I've already told you in a three phase three winding transformer, whatever we are going to assume that there are no losses ideally. So whatever the complex power input is equal to complex power load. So how much amount of complex power that we are going to give is equal to complex power absorbed by the load. So S primary is equal to S load. Then what is the value of the magnitude of the S primary is nothing but root 3 VL or 3 into V phase into I phase. We have to always take the magnitude values only. So complex power primary is nothing but root 3 into VL just you have to take the magnitude of the line voltage and the magnitude of the line current, or 3 into V phase into I phase, magnitude of the phase voltage into magnitude of the phase current. So this is the equation that you always have to remember. In the star connection, I have already told you the line voltage is equal to 2 times the phase voltage, and in the positive phase sequence, the line voltage is going to lead the phase voltage by plus 30 degree, and the line current is always equal to phase current. And what is the complex power? Complex power is equal to root 3 into VL into IL. All these are magnitude values, or simply 3 into V phase into I phase. All these are the magnitude values only we have to consider. All these are the magnitude values. So you can see clearly S is equal to root 3 into VL IL or 3 into V phase into I phase. All these are the magnitude values only we have to consider. In delta connection, I have already told you the line voltage is equal to phase voltage, and line current is equal to root 3 into phase current, and line current is going to lag the phase voltage by 30 degree. So minus 30 here. It is in the positive phase sequence. All these things I have already told you. And the complex power is equal to root 3 into VL into IL or 3 into V phase into I phase. All these are the magnitude values only. And the MMF balance is nothing but here N1 I1 bar is equal to N2 I2 bar plus N3 I3 bar. So MMF primary MMF is equal to, suppose let me assume there is a one primary and there are two secondary windings. So therefore the MMF is always balanced. Whatever the primary MMF is equal to the secondary MMF's addition. So N1 I1 bar is equal to N2 I2 bar plus N3 I3 bar. So N1 I1 bar is equal to N2 I2 bar plus N3 I3 bar. So this is a very important thing, that is every time based on these concepts in exams questions have been asked in a regular manner. So always in alternator, by default the connection is star, and by default the terminal voltage is given. I have already told you in alternator, whatever the armature coil present on the stator, always by default we are going to go for the star connection only, and whatever the voltage they are going to give you, it is basically the terminal voltage. So we can say that always in alternator by default the connection is a star, and by default the terminal voltage is given. I have already told you in an alternator always the armature coil within the stator will be always by default it will be in the star connection, and in the data they are going to give you the terminal voltage. Always in alternator by default they will ask the terminal line voltage only. See in the question they are asking voltage means it is a terminal voltage line voltage. So terminal line voltage they are going to ask in the alternator questions. So always in alternator by default they will ask the terminal line voltage only. For example, a 150 kVA 500 volt 3 phase star connected alternator. It means if we connect the rated load of 150 kVA and having terminal line voltage of 500 kV, then the rated line current is, we are going to get IL is equal to S by root 3 into VL. S is nothing but 150 into 2 10 to the power of 3 by root 3 into VL is 500. So what I am trying to say is, suppose in the question they are going to give you a rating in this manner, which is 150 kVA 500 volt 3 phase star connected alternator. So this is 150 kVA is nothing but it is a rated load that we can connect to this alternator. So if we connect a rated load of this one, it is going to have a terminal voltage of 500 volt. Then we can easily figure out the line current also. So therefore this is called as, whenever you apply a rated voltage, this is the terminal voltage and the rated line current you can easily figure out. A 150 kVA 500 volt 3 phase star connected alternator, it means that if we connect the rated load of 150 kVA and having a terminal line voltage of 500 volt, then the rated line current is nothing but S is equal to root 3 into VL. So IL is equal to S by root 3 into VL. So by this we are going to get the line current. So this is a very important point that you always have to remember. So this rating is going to tell you it is a rating of the rated load that you are going to connect, and also it is a terminal line voltage. So based on this we can easily figure out the line current, you can easily figure out. The basic aim of all the starting methods in induction motor is to increase the starting torque and decrease the starting current. I have already told you the basic agenda of all the starting methods in an induction motor is basically to increase the starting torque and also to reduce the starting current. So the basic agenda of all the starting methods in an induction motor is to increase the starting torque and decrease the starting current. So this is the basic function of all the starting methods in an induction motor. So now we will discuss some more about the different types of starting methods in the induction motor, and then different, we can see in-depth analysis of the starting methods in the induction motor. Now we are going to discuss in a detailed manner. So now we will discuss the different types of starting methods in induction motor. So this is called as the rotor circuit of the induction motor. It is a per phase. It is a per phase circuit diagram of the rotor circuit of induction motor. I have already told you this is R2, this is X2, and this is R2 into 1 by S minus 1. These things I have already told you. So this is R2, X2 and R2 into 1 by S minus 1. See, I have already told you torque is always directly proportional to the phase voltage whole square. So listen carefully. The torque is always directly proportional to phase voltage, the square of the phase voltage. What is the phase current? Phase current is equal to phase voltage by impedance of the coil, impedance of the stator impedance of the coil. So now you will see what is going to happen at the when we go for the dual starting, or you can say direct online, means directly you are going to give the supply. We are going to assume that the stator is connected in a delta fashion. So the stator winding is connected in a delta fashion. So at starting, what is going to happen? NR is equal to 0. The rotor speed is equal to 0. Then what is the value of slip? Slip is equal to 1. Slip is equal to 1. So whenever you keep 1 here, it is going to become short circuit. It is going to become short circuit. You can see clearly here, whenever S is equal to 1, it is going to become 0, means it is short circuit. So this is basically short circuit. Then the stator is always connected in the delta fashion. I have already told you in this, the stator is always connected in the delta fashion. Then the phase voltage is equal to line voltage is equal to V, because we are going to assume the line voltage is equal to V. So in always delta, the phase is equal to line. So therefore phase is also equal to V. Then what is the starting current through phase current? Or we can say what is the starting current through phase winding? So which is the phase voltage by phase impedance. So impedance of the coil. So let me assume the impedance is equal to ZSC. ZSC is called as the impedance of the coil. Impedance of the coil. So therefore, or we can say starting impedance. The starting impedance of the coil. The starting impedance of the coil is ZSC, which is equal to phase voltage is nothing but V. So V by ZSC. Then what is the line current? Then the starting line current is equal to root 3 times the phase current, because in a DOL and delta, always line current is equal to root 3 into phase. So we are basically seeing at the starting condition only. So starting current, the starting line current is equal to root 3 into starting phase current, which is root 3 into V by ZSC. Here ZSC is nothing but it is a winding. It is a winding of the stator at the initial condition, which is nothing but R2 plus JX2, because it is become short circuit. So we are going to get R2 plus JX2, because NR is equal to 0. So we are going to get slip is equal to 1. These things I have already told you. So now we will see what is going to happen for star delta starter. For star delta starter, I have already told you here we are going to keep here NR is equal to 0. Means starting condition means NR is equal to 0. Same thing I have already told you. Now we are going to connect initially we are going to connect the stator in the delta fashion. So stator is connected in the delta fashion. In the star, see, initially we are going to connect the stator in the star connection. In the star connection, line voltage is equal to root 3 into phase voltage and line current is equal to phase current. So now what is the phase voltage, which is line voltage by root 3, but line voltage is equal to V, so V by root 3. Then what is the phase current? Phase current is equal to line current. So therefore phase current is equal to phase voltage by impedance, which is phase voltage by impedance, which is ZSC. It's called as the starting impedance. Then what is the V phase? V phase is equal to V by root 3. So V by root 3 into ZSC is nothing but it is a starting line current, because in a star connection the line current is equal to phase current. So this is the current that you are going to get. Now after some time I am going to change into delta fashion. I will see what is the nature. Then the starting phase current is nothing but same thing. The starting phase current is nothing but phase voltage by impedance. Phase voltage is equal to V, so V by ZSC. Because in a delta fashion, phase voltage is equal to line voltage is equal to V. And what is the starting line current? Same thing we are going to get as the previous one, which is root 3 into phase current. So root 3 into phase current is V by ZSC. So this is the thing that you are going to get here. So now if we do the ratio of the line currents, basically the line currents we have to do the ratio. So the starting current, because the starting current of line with respect to star connection by starting current of line with respect to delta, it is nothing but 1 by 3 you are going to get. Same thing. So this is the thing that you are going to get here. Similarly, the starting torque with respect to star is equal to 1 by 3 times the starting torque with respect to delta. So finally I can say that very important point. Finally, because starting torque is nothing but it is directly proportional to phase voltage whole square. Then see phase voltage whole square. So this is an important point. You have to do the square of the phase voltage. So for star connection, the phase voltage is nothing but V by root 3. And for delta, the phase voltage is equal to V. So if we do the ratio, we are going to get like this 1 by 3. So finally I can say that the starting torque with respect to star delta starter is equal to 1 by 3 times the starting torque with respect to DOL. Similarly, the starting current with respect to start delta starter is equal to 1 by 3 times the starting current with respect to VOL. So this is a concept that you always have to understand. So now we go for the stator reactance method. So suppose if you are going to keep some reactance in the stator, so by using the stator we are going to reduce the per phase voltage. So V phase is equal to some x times of V. So S is going to lie between 0 to 1. Then what is the phase current? I have already told you. Phase current is equal to phase voltage by short circuit impedance or starting impedance, which is equal to phase voltage is nothing but x into V. So x into V by radius C. Then we can easily see, now we can get the ratio of the starting current. So now you can see what is the starting current. Starting current, I have already told you here, the ratio of the starting current of this one, the phase current itself in this one. See, in the stator reactance method, I am going to assume basically in the stator reactance method, I am going to assume it is connected in the delta fashion. It is always connected in the, see always, the stator is always connected in the delta fashion only. So, in the delta fashion, this is the phase current, then what is the line current? Line current is equal to 2 times the phase current. But we already know what is the line current in the delta that we have already know, which is root 3 into V by ZSC. So, if we do the ratio of these two things, then we are going to get X. So we can say the starting current by this stator reactance method is equal to X times the starting current through DOL connection. So listen carefully. In the stator reactance method also, basically we are going to give the stator is always connected in the delta fashion also. The stator reactance method also, the stator is always connected in the phase in the delta fashion only. But now the starting current, basically all these are line currents. So the starting current because of the stator reactance method is nothing but is equal to x times the starting current because of the DOL. Similarly, the starting torque is nothing but x square because starting torque is directly proportional to phase voltage whole square. If phase voltage is x into V, in the DOL it is V only. So therefore we are going to get square. If the ratio of these two things we are going to get square. So finally we can say the starting torque because of the stator reactance method is equal to x square times the starting torque because of the DOL connection. So this is what I am trying to tell you. So therefore the starting torque because of the stator reactance method is equal to x square times the starting torque because of the DOL connection. So now we will go for the auto transformer method. See, in the auto transformer method, same thing that we are going to happen. See, again the stator is in the star fashion only, in the delta fashion only. Again, only in the star delta method only we are going to keep initially the stator in the star and then we are going to convert into delta. In the remaining all the methods, the stator is always in the delta fashion only. So this is a very important point. Except only in the star delta starter only we are going to keep the winding, the stator winding in the start for initial and later we are going to change it into delta. In the remaining methods, all remaining methods, initially we are going to keep the we can say the stator winding in the delta fashion only. So therefore simply we can say that the starting torque of the auto transformer is equal to S square times the starting torque because of the DOL. So the starting torque because of the auto transformer is equal to X square times the starting torque because of the DOL. So this is the important point that you always have to understand. The starting torque because of the auto transformer is equal to X square times the starting torque because of the DOL. So now in the auto transformer method, listen carefully. The starting torque because of the auto transformer is equal to S square times the starting torque because of the DOL connection. And similarly, the starting torque with respect to star by the starting torque with respect to delta is equal to X square here. So X is called as the transformation ratio of the auto transformer. So this is a very important point that you always have to understand here. The starting current, the starting torque with respect to DOL is equal to X square times the starting torque with respect to the starting torque with respect to auto transformer is equal to X square times the starting torque with respect to DOL. And similarly, the starting current with respect to auto transformer is equal to X square times the starting current with respect to DOL. So, or in another case also I can say that here auto transformer is basically signifies that here whenever you connect a star and then a delta, then the ratio of the starting torque with respect to star by starting torque with respect to delta, you are going to get X square in auto transformer. Similarly, the starting current with respect to star connection by the starting current with respect to delta is equal to again X square you are going to get. This is called as the transformation ratio of the auto transformer. So you can connect in the initially in the star connection and then later in the delta connection. So this ratio with respect to auto transformer you are going to get as X square. Similarly, the starting current with respect to star by the starting current with respect to delta with the help of auto transformer we are going to get again X square. This is the significance of these two equations. X is called as the transformation ratio of the auto transformer. So X is called as the transformation ratio of the auto transformer. So through auto transformer, suppose through auto transformer you are going to supply to the stator. So whenever the stator is connected in star and then the stator is connected in delta, then the ratio of the star and delta is nothing but x square. Similarly, the starting current with respect to star by the starting current with respect to delta is equal to x square. Both these ratios are same for the auto transformer. So therefore, this called as a x is called as a transformation ratio of auto transformer. So now we will discuss another concept which is called as a referred to primary. So referred to primary is a very important concept. You can listen here, which is here. This is called as the L1 minus AM. This is AM, and this is A square L2 minus AM. It's a very important concept. So L1 minus AM. This is A into M, and this is A square L2 minus AM. So here, this is the circuit which is referred to the primary. Referred to the primary. So this is L1 minus AM. This is AM, and this is A square L2 minus AM. So L1 is called as the self-inductance of the primary winding. L1 is called as the self-inductance of the primary winding, and L2 is nothing but which is the self-inductance of the secondary winding. Then M is called as the mutual inductance between the primary and the secondary winding. Then L1 is called as the leakage inductance referred to primary, which is nothing but simply L1 minus A into M. Where A is called as the turns ratio. Basically, A is called as the turns ratio, which is N1 by N2. A is always equal to turns ratio, which is N1 by N2. So therefore, or simply we can say E1 by E2 also we can call. So A is nothing but turns ratio, which is N1 by N2 or E1 by E2. Similarly, L2 is called as a leakage inductance referred to primary side, which is simply A square into L2 minus A into M. Which is simply we can say that N1 by N2 whole square into L2 minus A into M. And here you have to use the A into M. So this is basically we can say L1 minus A into M, A square into L2 minus A into M, and this is A into M. So this is the important form that you always have to remember. This is L1 minus A into M, and this is basically A square into L2 minus AM, and this is AM. A is called as the turns ratio, and M dash is called as the A into M. So therefore we can say that M dash is called as the magnetizing inductance referred to the primary side. So M dash is called as the magnetizing inductance referred to the primary side. So finally I can say that here this is L1 minus AM, A square into L2 minus AM, and this is AM. So this is L1 is called as self-inductance of the primary winding, L2 is called as the self-inductance of the secondary winding, and M is called as the mutual inductance between the primary and the secondary winding, and L1 is called as the L1 is called as the leakage inductance referred to the primary side. So this is called as the leakage inductance referred to the primary side, and L2 is called as the leakage inductance referred to the primary side. Leakage inductance referred to the primary side, and M dash is called as the magnetizing inductance referred to primary side. Magnetizing inductance referred to the primary side. A is called as the turns ratio, which is A is equal to N1 by N2 is equal to E1 by E2. So this is the way that you always have to remember. So now we will discuss about the for single phase transformer. P is nothing but Vi cos phi, Q is equal to Vi sin phi, and S is equal to V into I. All these are the magnitude values. So for single phase transformer, P is equal to V into I cos phi, Q is equal to V into I sin phi, and S is equal to V into I. All these are the magnitude values. For three phase transformer, P is equal to root 3 into VL into IL cos phi, or 3 into V phase into I phase cos phi. Similarly, Q is equal to root 3 into VL into IL sin phi, or 3 into V phase into I phase sin phi, and S is equal to root 3 into VL IL, or 3 into V phase I phase. All these are the magnitude values we have to consider. So for three phase transformer, P is equal to root 3 into VL into IL into cos phi, or 3 into V phase into I phase cos phi, or Q is equal to root 3 into VL into IL sin phi is equal to 3 into V phase I phase into sin phi, and S is equal to root 3 into VL into IL, or 3 into V phase into I phase. This is for the three phase transformer, and this is for the single phase transformer. So let me give you a small summary. I have already told you the voltage rating and the current rating are always directly proportional to dimension square. Similarly, the KV rating is nothing but it's a product of the voltage and current. So it is a product of dimension square. Dimension square is nothing but dimension to the power of 4. Iron loss is directly proportional to volume of a core. So dimension whole cube. Volume has 3 dimensions, so dimension whole cube. Similarly, the we can say IC, the core loss component are working component, and I mu and I naught and L and XM, all these are directly proportional to dimension. So therefore, the voltage rating and current rating are always directly proportional to area. Area means dimension square, and KV rating is always directly proportional to voltage into current, which is dimension to the power of 4, and iron loss is always directly proportional to volume. Volume is 3 dimensions, so dimension to the power of 3, and working component and the core loss component are working component, the magnetizing current component, the no load current, and the inductance and the magnetizing reactance, all are directly proportional to dimension. So this is a very important point that you always have to remember these things. So voltage rating and current rating are always directly proportional to area. So therefore it is directly proportional to dimension square. And whereas the KV rating is directly proportional to voltage rating and into current rating, which is dimension to the power of 4. And the iron loss is always directly proportional to volume of the core. It means directly proportional to dimension to the power of cube. And the working component or poreless component, magnetizing current component, no load current component, and self-inductance and the magnetizing reactance, all are directly proportional to dimension. See, I have already told you, suppose this is a Z per unit old based on the S base old and the V base old. Similarly, Z per unit new based on the S base new and the V base new. Then what is the Z per unit new is equal to Z per unit old into here you have to use the formula like this. It is a very simple formula. You have to use the old, new, new. So this is the important formula. The Z per unit new is equal to Z per unit old into here V base old by V base new whole square into S base new by S base old. Easy way to remember is here old, here old, here old. This is square you have to do. These are the voltages and these are the, we can say these are called as the complex powers, PS values. So the Z per unit new is equal to Z per unit old into here we have to use the V base old by V base new whole square into S base new by S base old. So easy to remember is here it is old, here it is old, here it is old. The remaining two are new values, and here we have to use the voltage with respect to square. So finally Z per unit new is equal to Z per unit old into V base old by V base new whole square into S base new by S base old. So finally the Z per unit new is equal to Z per unit old into V base old by V base new whole square into S base new by S base old. So this is a very important formula. This is the Z per unit old based on the S base old and the V base old. Here this is the Z per unit new based on the S base new and the V base new. So Z per unit old new is equal to Z per unit new is equal to Z per unit old into V base old by V base new whole square into S base new by S base old. It's a very important formula. So for single phase transformer, I have already told you P is equal to V into I cos phi, Q is equal to V into I sin phi, and S is equal to V into I. All these are the magnitude values.